Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're drifting far beyond the familiar planets of our own solar system towards something so enormous, so strangely delicate, that when astronomers first saw evidence of it, many assumed there had to be some mistake. Because out there, orbiting a distant young star, may be a planet wrapped in rings so vast they make Saturns look like little more than decorative bracelets, and not just slightly larger either. We're talking about rings so enormous that if they replace Saturns, you would see them from Earth, with your own eyes stretching across the sky like glowing bands. Rings wide enough to swallow the distance between planets. Rings so large that calling them planetary rings almost feels inadequate, as though the universe accidentally started building a second solar system and then simply paused halfway through. The world at the centre of this impossible structure is called J1407b, which sounds less like the name of a majestic cosmic giant and more like a password your Wi-Fi router invents when it's feeling uncreative. And yet behind that very technical little label may hide one of the strangest planetary systems ever discovered. Somewhere tonight, while you're settling into bed or resting on a sofa or quietly staring at the ceiling, pretending you're going to sleep early for once, this enormous ringed world continues circling its distant star in silence. Its rings continue moving in slow motion, particle by particle, gap by gap, moon by moon, across distances so large the human brain almost refuses to process them properly. And perhaps that's part of what makes this story so oddly comforting. The universe, for all its violence and chaos, also builds things of astonishing patience, structures so enormous they take decades to shift noticeably. Ice and dust travelling carefully arranged paths around a young giant planet, forming patterns wider than entire planetary systems. No rushing, no urgency, just gravity performing its quiet work over immense stretches of time. Before we wander into those colossal rings together though, I'd love to ask you something. Where in the world are you listening from tonight? Maybe it's late evening where you are. Maybe the streets outside are quiet. Maybe there's rain tapping softly against a window. Or perhaps everything is still except for the occasional distant car drifting through the darkness. And what time is it right now in your little corner of Earth? Fitting questions, really. Because tonight's story is all about scale, about realizing that while we organize our lives around clocks, schedules, and hurried little routines, the cosmos is casually constructing structures so enormous they make our entire civilization feel like a passing blink. If you find this journey soothing, fascinating, or simply a nice way to slow your thoughts at the end of a long day, I'd be ever so grateful if you gave the video a like and maybe subscribed. It helps this calm little corner of science reach more wandering night owls, tired travellers, and curious minds searching for something peaceful before sleep. Now then, get comfortable. Dim the lights if you haven't already. Let your shoulders relax a little. And together, let's travel more than 400 light-years away from Earth toward a young star in the constellation Centaurus, where astronomers discovered something so unusual that even seasoned scientists briefly struggled to believe what they were seeing. Because this story doesn't begin with a photograph. In fact, that's one of the first surprising things about J1407b. Nobody has actually seen these rings directly in the way you might imagine. There's no dramatic telescope image showing a giant glowing planet wrapped in cosmic hoops floating majestically in space. Instead, the discovery began with flickering starlight, tiny changes in brightness, small dips and shadows hidden inside streams of astronomical data, which is wonderfully human if you think about it. So much of modern astronomy involves noticing when something behaves just slightly strangely. A wobble, a flicker, a dimming star. The universe rarely announces its secrets loudly. More often, scientists uncover extraordinary things because somewhere, somebody notices that a graph looks a bit odd on a Tuesday afternoon. In this case, the star in question was called V1400 Centauri, though astronomers often shorten it simply to J1407. A young star located roughly 434 light-years away from Earth. Young, in cosmic terms, means perhaps around 16 million years old, which sounds ancient until you remember our Sun is over 4.5 billion years old. So this entire system is still basically in its cosmic teenage years. Planets are still forming, material is still moving around chaotically, moons may still be assembling themselves from enormous disks of debris. It's a messy stage of life for a solar system. Rather like a teenager's bedroom, except instead of clothes scattered across the floor, it's trillions of tons of ice and rock orbiting giant planets. Back in 2007, astronomers monitoring this young star noticed something deeply unusual happening to its light. Over a period of weeks, the star dimmed repeatedly in bizarre patterns, not once, not smoothly, but over and over again, with complex changes in brightness that didn't match any ordinary planetary transit. Normally, when a planet passes in front of a star, the brightness dips in a fairly simple way. The planet blocks a portion of the light, then moves on. Clean, predictable, rather tidy by astronomical standards. But this event was different. The star's brightness fluctuated wildly for nearly 2 months. Imagine turning on a lamp while somebody repeatedly waves dozens of semi-transparent curtains in front of it. Some thick, some thin, some dense enough to block lots of light, others barely noticeable. That's roughly what astronomers were seeing, and immediately questions began piling up. What kind of object could possibly create such an enormous and complicated shadow? At first, scientists explored multiple explanations. Perhaps clouds of debris, perhaps unusual dust formations, perhaps something even stranger. But as researchers analysed the patterns more carefully, one explanation slowly rose above the others. A gigantic ring system. Not just large, absurdly large. The kind of structure that forces astronomers to start comparing things to entire solar systems, because ordinary planetary comparisons stop being useful surprisingly quickly. To understand just how extreme this is, we need to pause for a moment and talk about Saturn, because Saturn has thoroughly spoiled humanity's expectations when it comes to rings. Whenever we imagine planetary rings, we picture Saturn's elegant bands arching gracefully around the planet. They're enormous by human standards, around 280,000 kilometers across if you include the major rings. Beautiful, thin, bright. Probably the most recognizable planetary feature in the solar system besides Earth's oceans. But Saturn's rings, enormous as they seem to us, would look tiny beside those of J1407b. The proposed ring system around J1407b may stretch roughly 120 million kilometers across. That's nearly the distance from Earth to the Sun. Not the planet itself, mind you. The rings. You could fit Saturn and its entire ring system comfortably inside only a fraction of the structure surrounding J1407b. In fact, the rings are so vast that if Saturn possessed them instead, they would appear larger than the full moon in Earth's sky. It becomes difficult to even visualize properly after a certain point. Human brains evolved to estimate things like fruit size and whether large animals might eat us. We did not evolve to mentally process ring systems larger than planetary orbits. Somewhere around wider than the distance between worlds, intuition simply packs its bags and leaves. And still, the numbers become even stranger. Scientists believe the rings are composed of dozens upon dozens of separate bands, with enormous gaps carved between them. Those gaps may have been created by moons forming inside the rings themselves. Tiny young worlds slowly sweeping clean paths as they orbit through the surrounding material, which means astronomers may not simply have discovered giant rings. They may have caught a planetary moon system in the middle of being born. That possibility alone transformed J1407b from a curious observation into one of the most fascinating exoplanet candidates ever studied. Because in our own solar system, We see mature moons, stable moons, ancient moons that formed billions of years ago. But here perhaps we're witnessing the process itself still underway. Cosmic construction happening in real time, though real time in astronomy still involves waiting years for new data and occasionally arguing politely over graphs. There's another wonderfully strange detail here too. Scientists still aren't entirely certain what J1407b actually is. Most evidence suggests it's probably a giant gas planet, perhaps many times more massive than Jupiter. But because the object itself hasn't been directly observed clearly enough, some uncertainty remains. It could potentially sit somewhere near the blurry boundary between giant planet and brown dwarf, those odd in-between objects too large to be ordinary planets, but too small to fully ignite like stars. Astronomy loves categories right up until the universe casually creates something that ignores them. Still, regardless of its exact classification, one thing became clear very quickly. Whatever was orbiting that star was enormous, and young, and surrounded by material on a scale nobody expected. Interestingly, giant ring systems may actually be fairly common during the early stages of planetary formation. We simply rarely catch them at the right moment. Cosmic timing matters enormously in astronomy. Many structures exist only briefly before evolving into something else. The rings around J1407b are probably temporary. That sounds funny when discussing structures millions of kilometers wide, but temporary in astronomy simply means not lasting millions upon millions of years. Eventually, much of that material may gather into moons. Some may crash together, some may fall inward, some may escape entirely. In other words, we may be witnessing a short-lived phase of planetary evolution, a snapshot from a brief era in the life of a young giant world. That thought changes the emotional feeling of the system somehow. The rings stop feeling static and decorative and begin feeling active, transitional, like watching scaffolding around a building still under construction. Saturn's rings are graceful and mature. J1407b's rings feel unfinished, wild, young, still becoming something else. And yet even that description barely captures the scale involved. Imagine standing on a moon orbiting somewhere inside this system. The rings overhead would not resemble Saturn's delicate stripes. They would dominate the sky entirely. Vast glowing structures stretching from horizon to horizon, layered with dark gaps and brilliant dense bands of icy material reflecting distant starlight. Night might barely exist beneath them. The shadows alone would shape the environment of any moons inside the system. Temperatures would shift as giant ring bands blocked starlight overhead. Ice particles would drift endlessly through gravitational patterns established by moons, resonances and collisions happening across incomprehensible distances, and all of it moving silently. That's perhaps the strangest thing about space. The scale screams grandeur, but the experience itself would be utterly quiet. No roaring, no cosmic orchestra, just motion without sound, particle after particle orbiting patiently through darkness. It's also worth remembering how recent this discovery really is. For most of human history, we didn't know planets existed around other stars at all. The first confirmed exoplanets were discovered only in the 1990s. Since then, astronomers have uncovered thousands of alien worlds, hot Jupiters larger than Jupiter orbiting dangerously close to stars, lava planets with melting surfaces, ocean worlds, rogue planets wandering through interstellar darkness alone, and somewhere among them sits J1407b wearing rings so enormous they almost seem fictional, which says something wonderful about the universe itself. Reality consistently turns out stranger than the versions humans invent beforehand. We imagined planets. The cosmos produced planets with solar system-sized rings. We imagined moons. The universe built moons orbiting planets, orbiting binary stars. We imagined stable, neat systems. Nature answered with gravitational chaos and cosmic oddities beyond anything early astronomers could have predicted. And yet, despite all that complexity, discoveries like J1407b still begin with something remarkably simple. Somebody notices a star dimming. Somebody stays curious long enough to ask why. And slowly, patiently, piece by piece, an impossible structure emerges from the darkness. As scientists continued analysing the strange eclipses around J1407, the picture became increasingly detailed and increasingly bizarre. The dimming patterns suggested not merely a few rings, but dozens of them arranged in an enormous disk. Some dense, some thin, some separated by huge empty gaps, possibly carved by forming moons, sweeping material aside as they orbited. In other words, the rings were behaving less like decoration and more like a miniature solar system in progress. Back in 2007, while most of the world was busy with entirely ordinary Earth problems like forgotten passwords, delayed trains, and deciding whether putting avocado on everything counted as a personality trait, something deeply peculiar was unfolding 434 light-years away in the constellation Centaurus. A young star named V1400 Centauri began behaving in a way astronomers had never really seen before, not exploding, not pulsing, not vanishing dramatically into deep space. Instead, it flickered, and at first glance that probably sounds a bit underwhelming. Stars flicker all the time, at least from our perspective on Earth. Our atmosphere bends and distorts starlight constantly. Entire branches of astronomy are built around studying small variations in brightness, so initially there was no reason to assume this particular star would become famous. But then researchers looked more carefully, and the deeper they looked, the stranger things became. The brightness dips coming from J1407 were not behaving like normal planetary transits at all. Usually when astronomers discover an exoplanet using the transit method, the process is fairly straightforward. A planet crosses in front of its host star from our viewpoint, blocks a tiny portion of the starlight, and creates a smooth, predictable dip in brightness. Imagine a small insect slowly crawling across a flashlight beam. The light dims slightly, then returns to normal once the insect passes. Simple, neat, mathematically satisfying. Astronomers absolutely love mathematically satisfying things, but J1407 refused to cooperate with this tidy picture. Instead of one smooth, dimming event, the star's light fluctuated wildly over a period lasting nearly 56 days. Brightness levels rose and fell in complicated patterns. Some dips were deep, others were shallow. Some happened quickly while others stretched longer. The whole thing looked less like a single object crossing a star and more like somebody repeatedly dragging dozens of uneven, translucent curtains across a spotlight. Immediately, scientists realized this was not normal, and in astronomy, not normal is often where the fun begins. One of the most important things to understand about modern astronomy is that researchers usually do not discover alien worlds by seeing them directly. Space is simply too enormous and stars too bright. Trying to photograph an exoplanet next to its host star is a bit like trying to photograph a firefly beside a stadium floodlight from thousands of kilometers away. So instead, astronomers become detectives. They look for indirect clues, tiny stellar wobbles, gravitational shifts, drops in brightness, patterns hidden inside massive amounts of data. The transit method in particular has become one of the most successful techniques in exoplanet discovery. Thousands of worlds have been found this way. A planet passes in front of a star, and sensitive instruments measure the slight reduction in brightness. But J1407's brightness changes were unlike anything researchers had encountered before. For one thing, the eclipse event was enormous. A normal planetary transit might last hours, maybe a day or two, depending on the orbit and the size of the star. But this strange event stretched on for weeks, nearly 2 months of irregular dimming. That alone suggested whatever was passing in front of the star had to be absolutely gigantic. And then there was the complexity. Scientists analysing the light curve which is the graph showing brightness changes over time, noticed intricate structures inside the dimming pattern. There were sharp drops, gradual fades, multiple layers of shadowing, and repeated fluctuations that hinted at something highly organized rather than random clouds of dust. The data looked structured, engineered almost. Not artificial, of course. At least nobody seriously proposed alien megastructures, which is honestly impressive because the internet usually reaches that conclusion within approximately 6 seconds whenever astronomers describe something unusual. No, this looked gravitational. Orbital, layered. Eventually, researchers led by astronomer Eric Mamajek began proposing the explanation that would make J1407b famous, a colossal ring system, not merely larger than Saturn's, vastly larger. The scale was so extreme that even experienced astronomers had to pause and carefully check the math. Because if their interpretation was correct, this was not just another ringed planet. This was something entirely different, something operating on scales previously unseen around any planet. To appreciate why scientists reacted so strongly, it helps to understand how unusual Saturn already is. Saturn's rings are among the most spectacular structures in the solar system. Bright icy particles orbiting in broad flat bands around the gas giant. They span hundreds of thousands of kilometers, yet remain astonishingly thin in many places, often only tens of meters thick, and humans adore them. Saturn without rings would still be a magnificent planet, but the rings elevate it into something almost mythological. They transformed Saturn into the crown jewel of introductory astronomy textbooks. But Saturn's rings suddenly started looking rather modest once researchers estimated the size of the structures around J1407b. The proposed ring system around this distant world may stretch up to 120 million kilometers in diameter. That number hardly sounds real at first, so let's slow it down a little. Earth orbits the Sun at an average distance of about 150 million kilometers, meaning these rings approach the scale of the orbit of an entire planet. Another comparison helps even more. If Saturn possessed rings this large, they would dominate Earth's sky. Not as a small feature visible through telescopes, but as a gigantic luminous structure visible during daytime. You could glance upward and see them arching across the heavens. Suddenly, Saturn's familiar rings start feeling almost delicate by comparison. And yet what truly shocked astronomers wasn't only the size, it was the implication. Because ring systems this enormous are not expected to remain stable forever. In fact, they probably cannot. Which suggested scientists might be observing something temporary and incredibly rare. A developmental stage, a moment caught in progress. Researchers began suspecting the rings were actually part of a moon-forming disk surrounding a young giant planet. Inside those rings, material may slowly be clumping together under gravity, forming moons that eventually clear gaps through the disk as they orbit. And intriguingly, the light data seemed to support this idea. Several major gaps appeared inside the ring system. Those empty regions resembled the structures created by moons interacting gravitationally with surrounding particles. We already see similar processes in Saturn's rings. Tiny shepherd moons help maintain ring boundaries and create gaps through orbital resonances. Gravity sculpts the rings into organized patterns. But on J1407b, everything appears scaled up to astonishing proportions. Imagine taking Saturn's ring system and enlarging it until it approaches the size of a miniature solar system. That's the kind of scale researchers suddenly found themselves discussing in scientific papers. Naturally, this discovery created enormous excitement across astronomy. Because J1407b represented something more than simply a strange exoplanet, it potentially offered a glimpse backward in time. Our own giant planets likely passed through chaotic developmental stages billions of years ago. Jupiter and Saturn almost certainly possessed far larger circumplanetary disks during their youth, disks from which their moons eventually formed. But that era vanished long before humans existed. J1407b may have provided a rare opportunity to observe a similar process still underway around another star. Astronomers are deeply aware of how fortunate timing matters in science. The universe evolves slowly, sometimes frustratingly slowly. Galaxies take millions of years to noticeably change shape. Planet formation spans enormous timescales. Stars live for billions of years. Humans, by comparison, are brief observers, so catching a system during a transitional stage is extraordinary. It's like arriving at a construction site halfway through the building process rather than only seeing the finished structure centuries later. And there's another layer of strangeness here too. Scientists still do not completely understand the object at the centre of the rings. Most evidence suggests J1407b is probably a giant gas planet, perhaps 10 to 20 times the mass of Jupiter. But direct observations remain limited. The object itself hasn't been clearly imaged well enough to remove all uncertainty. It might instead occupy the blurry territory between giant planet and brown dwarf. Brown dwarfs are fascinating cosmic oddities. Too massive to be ordinary planets, but not massive enough to sustain full hydrogen fusion like proper stars. They exist in this awkward middle category astronomers sometimes jokingly call failed stars, which sounds rather harsh considering they're still gigantic, glowing balls of gas. Imagine being classified by your failure to ignite properly. Quite rude, honestly. Regardless of the exact classification though, the ring system itself remained the real headline, because nothing remotely similar had ever been documented before. And that forced astronomers into a slightly uncomfortable but exciting scientific position. They discovered something that did not fit neatly into existing expectations. Science progresses beautifully during those moments. Not because scientists enjoy being wrong exactly, although many secretly do appreciate a good surprise, but because anomalies force knowledge forward. Every major revolution in astronomy began with observations that contradicted assumptions. Planets moving strangely led to gravity theories. Unexpected Mercury orbital behavior contributed to relativity. Strange stellar dimming revealed exoplanets, and now, bizarre flickering around J1407 hinted at structures larger than anyone expected planets could possess. Interestingly, one reason the system shocked researchers so deeply is because planetary rings had always felt somewhat secondary in astronomy. Beautiful, certainly. Scientifically useful, yes, but still relatively small additions orbiting planets. J1407b changed that perspective. Suddenly, rings themselves became the dominant structure. The rings around this world are so large that the planet almost feels incidental by comparison. The central object exists mostly as the gravitational anchor, holding together an enormous rotating architecture of ice, rock, and dust. It's rather like discovering a cathedral and then realizing the supporting columns are planets. As more scientists examined the data, additional questions emerged. How common are giant ring systems in young planetary systems? Are we simply failing to notice them elsewhere? Could many young gas giants begin life surrounded by enormous moon-forming disks before eventually settling into smaller mature ring systems? And perhaps most intriguingly, how long do structures like this survive? The answer is probably not very long by cosmic standards. That's important because it means J1407b may represent an exceptionally lucky observation. These giant disks likely evolve relatively quickly. Material collides, gathers into moons, falls inward, or gets ejected outward. Over millions of years, the rings gradually disappear or transform, which means astronomers may have captured this system during a relatively brief phase, a temporary moment in planetary history. There's something oddly moving about that. Humans often think of astronomical objects as eternal because their timescales dwarf our own lives. Mountains seem ancient to us. Planets seem permanent. Stars feel immortal. But the universe changes constantly. Ring systems form and vanish. Moons migrate. Stars evolve, galaxies collide. Even structures spanning millions of kilometers may exist only briefly compared to the age of the cosmos itself. J1407b reminds us that planetary systems are not static displays frozen in place. They are active environments continuously reshaping themselves. And speaking of reshaping expectations, astronomers soon realized another challenge surrounding J1407b. The discovery itself was based primarily on a single major eclipse event. That's simultaneously exciting and frustrating. Exciting because the event revealed extraordinary detail. Frustrating because scientists desperately wanted more observations. Astronomy often involves long waits, and J1407b became a perfect example of this cosmic patience problem. Researchers searched carefully for repeat transits that might confirm orbital details and refine models of the ring system. But so far, no identical event has been observed again. That uncertainty complicated everything. Without repeated transits, estimating the exact orbit becomes difficult. Scientists still debate aspects of the system's geometry, orbital period, and even whether the object is gravitationally bound exactly as originally proposed. In other words, J1407b remains partly mysterious. And oddly enough, that uncertainty may have increased fascination with the system, rather than diminished it. Humans are naturally drawn toward incomplete stories. The unknown edges keep the imagination active. If astronomers had discovered a perfectly ordinary giant planet with perfectly ordinary rings, interest would have faded fairly quickly outside scientific circles. But J1407b sits in that wonderfully uncomfortable region, between observation and mystery. Large enough to seem unbelievable, documented enough to seem real, uncertain enough to remain intriguing. There's another reason the discovery captured public imagination too: scale. Humans struggle emotionally with astronomical distances because they become abstract very quickly. Light years blur together. Millions of kilometers stop feeling meaningful after a point. But rings larger than a solar system, that people can picture, at least emotionally, you immediately sense the absurdity of it. A planet surrounded by structures approaching planetary orbital scales feels mythic somehow. Less like ordinary astronomy and more like something science fiction writers would invent after several cups of coffee and a deadline. Except nature arrived there first, as it usually does. One particularly fascinating aspect of the discovery involves the speed at which the ring material must move. Different parts of the rings orbit at different velocities depending on their distance from the central object. Inner regions move faster, outer regions slower. Across a structure tens of millions of kilometers wide, those orbital dynamics become incredibly complicated. Gravity creates resonances, gaps, wave patterns, dense clumps. The rings are not static hoops suspended motionless in space. They are dynamic flowing systems composed of countless particles constantly interacting. In many ways, giant rings resemble flattened miniature solar systems. That realization alone transformed how astronomers viewed the discovery. And somewhere inside all that motion, perhaps moons were forming. Young icy worlds gradually assembling themselves from orbiting debris around a distant giant planet. The thought is remarkable because it means we may not simply be observing rings, we may be observing planetary evolution itself happening in front of us. Of course, the universe rarely provides answers cleanly. Every proposed explanation surrounding J1407b opened additional questions. If the rings are so enormous, why haven't they collapsed already? How massive must the central object be to stabilize them? What mechanisms maintain the gaps? Could multiple moons already exist inside the disk? And perhaps most importantly, what would such a ring system actually look like up close? For a very long time, humanity believed Saturn represented the upper limit of what a ring system could become. Not officially, perhaps. Scientists are usually careful about declaring anything impossible, because the universe enjoys embarrassing certainty. But emotionally, Saturn felt complete. Its rings were already so elegant, so enormous, and so visually overwhelming that they seemed almost excessive. Surely nature did not need to go any further than that. And then J1407b arrived and casually shattered that assumption like a dropped wine glass in a quiet kitchen. Because the moment astronomers began estimating the true scale of the proposed rings surrounding J1407b, the numbers stopped sounding like planetary science and started sounding like somebody had accidentally added extra zeros during calculations. At first, even researchers approached the estimates cautiously. That's common in astronomy whenever something appears too extreme. Scientists become suspicious of their own results, instruments are checked, data gets reanalyzed, assumptions are challenged repeatedly. Nobody wants to announce the discovery of the largest ring system ever observed, only to discover later that a telescope was having a very expensive misunderstanding. But the evidence kept pointing in the same direction. The structure surrounding J1407b appeared absolutely colossal, not merely larger than Saturn's rings, hundreds of times larger. To appreciate how shocking this truly is, we need to spend a little time with scale, because the universe has an annoying habit of making gigantic things sound deceptively manageable when converted into neat scientific numbers. For example, Saturn's main ring system stretches roughly 280,000 kilometers across. That already feels huge. You could line up more than 22 Earths side by side across Saturn's rings. If those rings suddenly appeared around Earth, they would dominate the sky entirely. They would become the defining feature of human civilization overnight. Every culture, religion, poem, airline advertisement, and awkward tourist selfie would involve the rings somehow. And yet Saturn's magnificent system begins looking strangely modest beside J1407b. The proposed ring system around this distant world may span roughly 120 million kilometers, not 1,000, million. That distance approaches the orbital scale of planets themselves. To put it another way, if you place the Sun at the center of these rings, the outer edge would extend a substantial portion of the way toward Earth's orbit. Imagine looking at Saturn through a telescope and realizing the rings are not just surrounding the planet but stretching outward across distances comparable to the space between worlds. It feels almost unreasonable, like nature ignored the usual rules of proportion entirely. And this is precisely why astronomers reacted with such disbelief initially. Planetary rings, at least in our experience, simply were not supposed to become this large. There are practical reasons for that. Ring systems exist inside something called the Roche limit, which sounds vaguely like a French detective, but it's actually a gravitational boundary. Inside this region, tidal forces from the planet prevent material from clumping together into larger bodies. Rocks and ice remain dispersed, forming rings rather than moons. Outside the Roche limit, however, gravity begins encouraging material to gather into larger objects. Moons form, particles collide and merge. The ring system gradually transforms into something else. That's why Saturn's rings remain relatively compact compared to planetary orbits. So immediately J1407b created a puzzle. How could a ring system remain stable across such enormous distances? The answer may lie in the fact that we are not looking at a mature, stable ring system like Saturn's at all. Instead, astronomers believe we may be witnessing something much younger and far more chaotic. A circumplanetary disk. Essentially a giant rotating structure of debris surrounding a young, massive planet where moons are actively forming. That distinction matters enormously. Saturn's rings are comparatively refined, mature, delicate. J1407b's rings appear more like a construction zone, a gigantic swirling disk still in the middle of becoming a moon system. And honestly, that makes the discovery even more fascinating, because it means the structure is not merely decorative, it's evolutionary, dynamic, transitional. When scientists studied the brightness variations from V1400 Centauri, they identified evidence for dozens of distinct ring layers. some dense enough to block substantial amounts of starlight, others thinner and more transparent. Between them lay large gaps, likely carved out by newly forming moons orbiting through the disk. In many ways, it resembles a miniature solar system assembling itself, except the miniature part stops applying once you realise the entire structure dwarfs anything humans have ever seen around a planet before. There's something deeply strange about that scaling effect. Human intuition keeps trying to compare J1407b's rings to Saturn, because Saturn is our reference point. But eventually the comparison breaks down completely. It's like comparing a bicycle to a continent because both technically occupy space. The systems operate on entirely different levels. One helpful comparison astronomers often use involves our own moon. If Saturn's rings replaced Earth's moon in the sky, they would appear astonishingly large and bright. But if J1407b's rings surrounded Saturn instead, they would stretch across enormous portions of the sky, visible even during daytime. They would no longer look like rings, they would look like architecture, gigantic luminous bands arcing overhead from horizon to horizon. Imagine ancient humans living beneath skies dominated by structures like that. Astronomy itself would have developed differently. Mythology would have changed. Calendars, navigation, religion, even the emotional relationship between humans and the night sky might have evolved along entirely separate paths, because giant rings would constantly remind you that you live inside a gravitational system. We tend to think of planetary orbits as abstract diagrams in textbooks because we cannot directly see Earth's orbital structure. But beneath enormous rings, gravity becomes visible. Orbital mechanics become part of daily life. And somewhere in that thought sits one of the most remarkable aspects of J1407b. It transforms invisible cosmic processes into something almost imaginable. Not fully understandable, perhaps, but imaginable. The scale also shocked astronomers because maintaining structures this large is incredibly difficult. Orbital systems become unstable over time, collisions occur, material disperses, moons emerge and reshape the disk gravitationally. Everything in space is moving constantly. That's important to remember because rings often look static in illustrations. Nice clean circles frozen around planets like decorative ornaments. Real ring systems are more complicated. They are flowing environments composed of trillions upon trillions of particles ranging from microscopic dust grains to objects the size of houses or mountains. Every piece moves under gravity's influence. Every orbit interacts subtly with neighbouring material. Inside Saturn's rings, waves ripple outward due to gravitational resonances with moons. Spiral patterns emerge. Gaps shift slowly over time. Tiny moonlets disturb nearby particles like boats moving through water. Now enlarge that entire process to scales approaching planetary orbits. That's the kind of environment scientists believe may exist around J1407b. And because the system is young, things are likely even messier. Young planetary systems are chaotic places. Material crashes together constantly. Orbits evolve. Gravity reshapes everything repeatedly. Stable configurations emerge only gradually over millions of years. Our solar system probably looked similarly violent long ago. Jupiter and Saturn almost certainly possessed enormous disks during their youth. Their moons likely formed inside those disks much the same way planets form around stars. But humans arrived billions of years too late to witness that stage directly. J1407b may have offered astronomers a rare glimpse into a process normally hidden in the deep past of mature solar systems, which means this discovery is not simply about giant rings, it's about cosmic history, about seeing how planetary systems build themselves. There's another reason the scale proved so emotionally powerful too. It challenged assumptions about where meaningful boundaries exist in astronomy. Humans naturally organize the universe into categories. Planets here, rings there, moons somewhere between, nice tidy labels. But J1407b blurred those distinctions. Its rings are so enormous that they begin functioning more like independent orbital systems than traditional planetary rings. Moons forming inside the disk resemble planets forming around stars. The same physical processes appear again and again across different scales. Gravity is wonderfully repetitive that way. Stars form from disks. Planets form from disks. Moons form from disks. Nature keeps recycling the same basic strategies across the cosmos, and occasionally it produces structures so extreme they reveal those similarities more clearly than ever before. One especially fascinating detail involves orbital speed. Objects closer to the central planet orbit faster than those farther away. This creates enormous internal complexity across such a gigantic ring system. Inner regions may complete orbits relatively quickly while outer portions move much more slowly. Imagine traffic moving at wildly different speeds across lanes spanning millions of kilometers. Now add gravity, and collisions, and forming moons, and tidal interactions. The result is not a static disk, but a constantly evolving gravitational ecosystem. Astronomers studying the light data noticed evidence suggesting over 30 separate ring layers. Some may have been extremely dense, others relatively sparse. The gaps between them varied dramatically too. One particularly large gap may indicate a moon with roughly Earth-like mass already forming within the disk. Pause for a moment and appreciate how extraordinary that possibility really is. A moon forming inside rings larger than a solar system around a giant planet hundreds of light years away. And humans detected all this from tiny changes in starlight. There's something almost absurdly clever about astronomy sometimes. We often picture science as involving giant dramatic machines producing instant discoveries. But many breakthroughs actually emerge through patience, careful analysis, statistical modelling, looking at graphs until patterns begin revealing hidden structures. Astronomers never physically travelled to J1407b. Nobody saw the rings directly sweeping across the star. Instead, scientists reconstructed the system mathematically from shadows. That fact alone makes the discovery feel strangely elegant. Like reconstructing an entire cathedral from the shape of sunlight passing through stained glass. And still, despite all these calculations, uncertainties remain. Because the system is so unusual, many details remain debated. Researchers continue refining models of the ring structure, orbital dynamics, and central object. Some aspects of the system may change as additional observations emerge in future years. Science often works this way. Discoveries arrive incomplete, messy, partially understood, especially when dealing with objects so far beyond ordinary experience. Interestingly, J1407b also forced scientists to reconsider how common giant ring systems might actually be in the universe. Perhaps such disks are normal during early planetary development. Maybe young giant planets frequently possess enormous circumplanetary structures, while moons assemble themselves. If so, we simply rarely observe them, because the timing must align perfectly. The ring system must pass directly between us and the star. The star must be monitored continuously. The dimming pattern must be detailed enough for interpretation. Astronomy depends heavily on fortunate geometry. Entire discoveries occur because objects happen to align correctly from Earth's viewpoint. There's something humbling about that. Human knowledge sometimes advances not because the universe intentionally reveals itself, but because cosmic objects accidentally line up in convenient ways while we happen to be paying attention. And occasionally, when everything aligns just right, we uncover something astonishing. Like a ring system so large it no longer feels planetary. Of course, enormous scale alone does not guarantee permanence, in fact, quite the opposite. One reason the rings around J1407b seem so shocking is because structures this large are probably unstable over long timescales. Material eventually gathers into moons or disperses outward. gravitational interactions gradually reorganize the system, which means these rings may represent a temporary phase, a brief transitional moment. That idea changes the emotional feeling of the discovery slightly. Instead of viewing the rings as permanent architecture, we begin seeing them as motion frozen in progress, a system actively evolving before our eyes. Somewhere inside those rings, moonlets may already be clearing paths, tiny worlds slowly emerging from collisions and accumulated ice. Over millions of years, the giant disk could shrink dramatically as material reorganizes itself into stable satellites. Eventually, perhaps, the system may resemble something closer to Jupiter or Saturn, with mature moons and smaller remaining rings. But right now, at this moment in cosmic history, it exists in its giant unfinished state, and that temporary nature somehow makes the system feel even grander. Humans tend to associate permanence with importance, but astronomy often teaches the opposite lesson. Some of the universe's most spectacular phenomena exist only briefly. Supernovae, planet-forming disks, colliding galaxies, young ring systems. Beauty in the cosmos is frequently transitional. There's also something strangely comforting about realizing that scale does not guarantee stability. Even structures spanning millions of kilometers still evolve, shift, and eventually disappear. The universe is dynamic everywhere. From weather systems on Earth to ring systems around distant planets, nothing remains perfectly fixed forever. And perhaps that's part of why J1407b captured imagination so powerfully. It showed us something enormous, not as a finished monument, but as a process still unfolding. A giant world wrapped in rings larger than anyone thought possible, quietly assembling moons in the darkness while orbiting a young distant star. A reminder that the cosmos still builds things beyond our expectations. Long before humans ever discovered J1407b, we imagined astronomy as something fairly direct. You point a telescope at the sky, you see a planet, you take a picture, done. Simple, very satisfying. The universe, unfortunately, had other plans, because the overwhelming majority of worlds beyond our solar system are so distant, so faint, and so thoroughly drowned in the glare of their stars that actually seeing them directly is extraordinarily difficult. A star outshines its planets by ridiculous amounts. Trying to photograph an exoplanet beside its host star is often compared to trying to spot a firefly hovering next to a lighthouse from thousands of kilometers away. And honestly, that comparison might still be too generous. So modern astronomy became less like sightseeing and more like detective work. Astronomers hunt for clues, tiny wobbles, microscopic brightness shifts, subtle distortions hidden inside oceans of data. And when it comes to detecting rings around a distant planet, especially rings larger than anything previously imagined, scientists rely on one of the strangest and most delicate forms of observation humanity has ever invented. They study shadows. That's really what much of exoplanet astronomy comes down to. Watching stars continuously and waiting for something to pass in front of them. A planet crosses the star from our perspective, blocks a small portion of the light, and creates a measurable dimming event known as a transit. At least in theory, the process is straightforward. Imagine turning on a bright lamp in a dark room. Now slowly move a marble across the front of it. The light dims slightly while the marble passes by. That tiny reduction in brightness is essentially what astronomers look for when searching for exoplanets. Except instead of marbles and lamps, we're dealing with planets hundreds of light years away, and brightness changes so small they often measure less than 1%. Human eyes could never detect such tiny fluctuations directly. Fortunately, telescopes do not get distracted halfway through observations because they suddenly remembered an embarrassing conversation from 6 years ago. Computers are wonderfully patient that way. Over the past few decades, astronomers developed incredibly sensitive instruments capable of monitoring stellar brightness continuously for months or even years. Missions like Kepler Space Telescope revolutionized this process by staring at enormous numbers of stars simultaneously and searching for recurring dimming events. The resulting data appears as something called a light curve. A light curve is simply a graph showing how the star's brightness changes over time. Most stars remain relatively steady, but if a planet passes in front of the star, a dip appears in the graph. A normal planetary transit produces a fairly clean shape. Brightness decreases gradually, reaches a low point, then rises again as the planet moves away. Rather elegant, very mathematically tidy. Astronomers adore tidy graphs. A clean transit signal is practically the scientific equivalent of discovering your kitchen somehow cleaned itself overnight. But then systems like J1407 arrived and ruined everyone's neat expectations. Because the light curve from V1400 Centauri did not look clean at all. It looked chaotic. Instead of a single smooth dip, the star's brightness fluctuated repeatedly over nearly 56 days. Some dimming events were shallow, others deep. Brightness rose and fell in complicated sequences. Sharp transitions appeared beside gradual fades. The graph resembled a mountain range more than a planetary transit. At first, astronomers naturally considered simpler explanations: dust clouds, stellar activity, debris fields, instrument problems. Scientists are trained to distrust extraordinary conclusions initially, because history contains many examples of discoveries later explained by far more ordinary causes. Telescopes malfunction. Data processing introduces errors. Cosmic rays hit detectors unexpectedly. The universe does not owe us simplicity. Still, the more researchers analyze the J1407 light curve, the more the evidence pointed towards something structured. Not random dust, not instrument noise, something organized, layered, orbital. Eventually, scientists realized the fluctuating brightness pattern could be explained remarkably well by a gigantic ring system crossing in front of the star. And this is where things become wonderfully intricate. Because detecting rings through transits is far more complicated than detecting planets alone. A planet creates one main shadow. Rings create many. Different ring layers possess different densities. Some block more starlight than others. Gaps between rings allow additional light through. Thin regions produce subtle dimming, while dense bands create deeper shadows. As the rings move across the star, each layer affects the brightness differently. The resulting light curve becomes enormously detailed. Imagine shining a flashlight through dozens of semi-transparent curtains suspended in motion. Thick curtains block lots of light. Thin curtains only dim it slightly. Open spaces let brightness return briefly before the next layer arrives. That's essentially what astronomers saw in the J1407 data. The light curve acted almost like a fingerprint for the ring system. By studying the timing and depth of brightness variations, scientists could reconstruct the likely arrangement of the rings themselves. That idea still feels almost magical somehow. Human beings sitting on a small rocky planet around an ordinary yellow star managed to infer the existence of colossal rings, orbiting another world hundreds of light years away simply by analysing flickering starlight. Astronomy often feels less like looking outward and more like listening carefully to whispers. One particularly important detail involves timing. The speed at which brightness changes occur helps scientists estimate how fast the transiting object moves. Faster motion creates shorter features in the light curve. Slower movement stretches events over longer periods. By combining transit duration with orbital mechanics, astronomers can begin estimating the size of the ring system itself. And in the case of J1407b, those calculations quickly became astonishing. Because the transit lasted far too long for an ordinary planet, something enormous had to be crossing the star. Not only enormous, but structured with incredible complexity. researchers eventually proposed models involving dozens of distinct ring layers extending across tens of millions of kilometers. That's the key moment when J1407b stopped being merely interesting and became extraordinary. There's another challenge too. Stars themselves are not perfectly stable. Young stars especially can fluctuate naturally. They produce star spots, magnetic activity, stellar flares, and brightness variations unrelated to planets. So astronomers must carefully separate stellar behavior from transit signals. This requires statistical analysis, repeated observations, and lots of caution. The scientific process is much less dramatic than movies often portray. Most discoveries involve researchers quietly arguing over graphs while consuming alarming quantities of coffee. Nobody dramatically gasps and whispers, "My God!" Usually somebody says something more like, that's odd. And then the next several years disappear into data analysis. In J1407b's case, astronomers created computer simulations testing different possible ring configurations. By adjusting ring density, spacing, orbital speed, and geometry, they searched for models capable of reproducing the observed light curve. Think of it like reverse engineering a machine after only seeing its shadow. The ring interpretation matched surprisingly well. In fact, some transitions in brightness appeared sharp enough to indicate defined ring edges, much like the distinct bands seen in Saturn's rings. Other regions suggested large gaps likely carved by forming moons orbiting inside the disk. And this is where detecting rings becomes even more scientifically valuable than simply finding them. The structure of the light curve may reveal the presence of moons that cannot be directly observed themselves. A moon orbiting inside a ring system affects surrounding material gravitationally. It clears gaps, reshapes particle distributions, and creates orbital resonances. Those structures then alter the brightness pattern during transits. In other words, astronomers can potentially detect unseen moons indirectly through the fingerprints they leave inside the rings, which is deeply impressive when you pause and think about it. We're talking about identifying gravitational effects inside a giant disk orbiting a distant unseen object around another star. And humans accomplished this while sitting safely on Earth, wearing sweaters and occasionally forgetting where we left our keys. Science is extraordinary sometimes. Interestingly, detecting ring systems around exoplanets is extremely difficult compared to detecting planets themselves. The geometry must align almost perfectly. The ring system has to tilt at an angle, allowing substantial portions to pass across the star from our viewpoint. If the rings are edge-on, they become nearly invisible. If the orbital alignment misses Earth entirely, no transit occurs at all. Most planetary systems likely remain forever hidden from transit detection, simply because their orientations are unfavourable from our perspective. Astronomy depends heavily on luck. Cosmic luck specifically. Objects must align across enormous distances with astonishing precision before humans can detect subtle transit signals. J1407b happened to align in exactly the right way at exactly the right time while astronomers were monitoring the star. That fortunate timing matters because giant ring systems may not last very long by cosmic standards. The enormous disk around J1407b is probably temporary. Over millions of years, material may gather into moons or disperse. The structure evolves continuously, meaning astronomers may have captured a brief developmental stage that most systems pass through unseen. That possibility makes the discovery feel strangely precious. Not because the system itself cares whether humans observe it, of course. The rings would continue orbiting perfectly happily regardless of our existence. But from a scientific perspective, catching a planetary system during an active moon-forming phase is extraordinarily valuable. It's a glimpse into the past of our own solar system. Jupiter likely possessed giant circumplanetary disks billions of years ago while its moons formed. Saturn almost certainly did too, but humans arrived far too late to witness those stages directly. J1407b may provide a living example of those ancient processes still underway elsewhere. And all of that knowledge emerged from light curves, from shadows, from watching a distant star flicker strangely for several weeks. There's also something beautifully indirect about this method of discovery. Humans did not conquer the distance to J1407b physically. We cannot travel there, we cannot send probes, we cannot photograph the rings clearly with current technology. Instead, we infer, we model, we reconstruct. Astronomy often resembles archaeology performed with mathematics. Scientists take tiny fragments of information and carefully build coherent explanations around them, and occasionally those explanations reveal structures beyond anything previously imagined. Another fascinating complication involves orbital period. Since astronomers observed only one major eclipse event from J1407b, determining the precise orbit remains difficult. Researchers continue searching for repeat transits that could confirm orbital timing and refine models of the system. But giant orbits may take many years, meaning astronomers must wait patiently. Space science often requires uncomfortable amounts of patience. You cannot hurry planets. You cannot politely ask giant ring systems to transit again at more convenient intervals. The universe operates entirely on its own schedule. Still, even with limited observations, the ring interpretation remains one of the most compelling explanations ever proposed for the system, and it opened an entirely new possibility in astronomy. If rings this large can exist around young giant planets, perhaps similar systems are common throughout the galaxy. Maybe many exoplanets begin life surrounded by enormous disks, where moons assemble themselves gradually. Perhaps our own solar system once looked similarly dramatic before billions of years of evolution reshaped everything into calmer, mature configurations. There's a humbling quality to that realization. We tend to think of the solar system as normal because it's familiar. But familiarity is not the same thing as typicality. The universe may produce structures far stranger and grander than anything surrounding our own sun, and sometimes detecting those structures requires little more than patience, precision instruments, and the willingness to investigate a star behaving just slightly oddly. One of the loveliest aspects of astronomy is that immense discoveries often begin with tiny discrepancies. A small wobble in a star's motion reveals a hidden planet. A faint dimming uncovers an alien atmosphere. A bizarre light curve exposes rings larger than a solar system. The universe hides enormous things inside very small signals. Sometime in 2007, a young star sitting quietly in the constellation Centaurus began doing something deeply inconvenient for astronomers. It stopped behaving normally. Not dramatically at first. There was no explosion, no enormous flare visible across the galaxy. No cinematic cosmic catastrophe sending nearby planets spiraling into darkness while orchestral music played in the background. Instead, the star simply began flickering in a strange way. And honestly, that is often how astronomy works. The universe rarely announces discoveries with fireworks. More commonly, it whispers through tiny irregularities buried inside spreadsheets and graphs, while exhausted researchers stare at computer screens, wondering whether they accidentally broke the data processing software again. The star itself, V1400 Centauri, was not especially famous before this event. A young star roughly 434 light-years away from Earth, still early in its cosmic life, quietly existing among countless others in the southern skies. Young stars tend to be somewhat unruly compared to older stars like our Sun. They rotate faster, produce stronger magnetic activity, throw tantrums in the form of flares and variability. Astronomers are accustomed to young stars acting unpredictably from time to time, rather like energetic puppies that have suddenly discovered furniture. So initially, the unusual flickering around J1407 did not immediately scream historic discovery. But then the dimming continued, and continued, and continued, Days passed, then weeks. The brightness of the star kept changing in complicated patterns, unlike anything researchers expected from an ordinary planetary transit. A normal exoplanet transit is beautifully simple. A planet crosses in front of its star, blocks a small amount of light, and creates a clean, symmetrical dip in brightness. The planet moves on, and the star returns to normal. Astronomers adore these tidy transits because they're predictable and relatively easy to analyze. One smooth dip tells you quite a lot already. Planet size, orbital timing, sometimes even atmospheric properties. But what unfolded around J1407 looked more like the star was passing behind a gigantic moving barcode made by somebody with deeply chaotic organizational habits. Brightness dropped sharply, then partially recovered, then dimmed again. Some sections were darker than others. Some transitions happened suddenly while others stretched gradually over time. The entire event lasted nearly 56 days. 56 days. That number alone immediately signaled that something extraordinary was happening. Even giant planets do not normally create eclipse events lasting nearly 2 months. Whatever crossed in front of the star had to be enormous, not simply large, astronomically absurd. And there's something wonderfully suspenseful about this stage of scientific discovery because nobody knows the answer yet. Researchers only know the universe is misbehaving somehow. Imagine sitting in a quiet observatory office late at night, watching incoming brightness data from a distant star, and realizing the graph keeps producing structures that make no immediate sense. At first, you probably suspect the instruments. Astronomers are careful people. Before proposing exotic explanations, they check the ordinary ones repeatedly. Telescopes malfunction. Detectors glitch. Atmospheric interference contaminates measurements. Computer systems occasionally behave like caffeinated raccoons pressing random buttons. So scientists began checking everything carefully. The data remained consistent. The flickering was real, and that's the moment things became exciting. Because real, unexplained astronomical behavior is essentially catnip for scientists. Researchers started analyzing the light curve in detail. A light curve, despite sounding vaguely poetic, is simply a graph showing changes in brightness over time. Normally these curves are fairly smooth during planetary transits, but the J1407 light curve looked wildly complicated. It contained dozens upon dozens of fluctuations layered together. Some dimming events blocked huge amounts of starlight, others only slightly reduced brightness. At times the star faded dramatically, then brightened again before dimming once more. The pattern resembled overlapping shadows, structured shadows. That distinction mattered enormously. Random dust clouds would likely create messy, irregular dimming without coherent organization. But the brightness changes around J1407 suggested geometry. Layers, orbital structure, something arranged. Eventually astronomers began exploring a startling possibility. What if the star was being eclipsed not by a planet alone, but by a gigantic ring system surrounding a planet? Suddenly the bizarre light curve started making more sense. Different rings could block different amounts of light depending on density. Gaps between rings would allow brightness to return temporarily. Thin regions would produce shallow dimming, while dense bands would create deeper shadows. The complex brightness fluctuations fit surprisingly well with the idea of an enormous layered disk crossing in front of the star. And once researchers began estimating the scale required to produce such a long eclipse event, the situation became genuinely shocking, because the rings had to be enormous beyond ordinary planetary standards, not Saturn-sized, much larger, the kind of scale that forces astronomers to stop comparing structures to planets and start comparing them to solar systems instead. Still, during those early stages, scientists remained cautious. Extraordinary claims require extraordinary evidence. That phrase appears frequently in science because humans are very good at accidentally convincing themselves of exciting things. Astronomy especially has a long history of mistaken interpretations, canals on Mars, non-existent planets, signals later explained by equipment problems. Nobody wanted J1407b to become another entry in the long proud tradition of, oops, never mind. So researchers began testing alternative explanations carefully. Could the flickering come from stellar activity alone? Unlikely. Could enormous dust clouds explain the observations? Not convincingly. Could multiple objects be crossing the star simultaneously? Possible, but difficult to reconcile with the detailed structure of the light curve. Again and again, the ring interpretation remained one of the best explanations available, and slowly, almost reluctantly, astronomers started realizing they may have uncovered something unprecedented. A giant world wrapped in rings larger than anything previously observed. There's a very human moment hidden inside discoveries like this. At some point, somebody in a research group quietly understands the implications before everyone else fully processes them emotionally. A realization forms. If this interpretation is correct, this thing is enormous. And then comes the difficult task of convincing yourself you're not misunderstanding the universe. Because honestly, the numbers sounded ridiculous. The proposed ring system around J1407b appeared capable of stretching roughly 120 million kilometers across. That's the sort of distance where the brain stops generating proper intuition and instead produces vague internal noises of concern. For comparison, Saturn's rings suddenly became tiny. Beautiful, certainly. Still magnificent. But tiny beside this thing, and the light curve implied not merely one broad ring, but many separate layers. Dense bands alternating with enormous gaps likely sculpted by forming moons. Researchers studying the data identified evidence for over 30 distinct ring structures. 30. Imagine watching shadows from dozens of enormous orbital bands sweep across a distant star for nearly 2 months. That's what astronomers were trying to reconstruct mathematically from flickering starlight. One especially intriguing aspect involved the sharpness of certain transitions in brightness. Some dimming changes happened rapidly enough to suggest clearly defined ring edges. That's important because sharp boundaries usually imply gravitational organization. Something was shaping the rings, maintaining structure, possibly moons embedded within the disk itself, and suddenly the discovery became even more fascinating. Scientists were no longer merely discussing giant rings, they were potentially observing moon formation in progress. That idea transformed J1407b into something much larger scientifically than a strange curiosity. Our own solar system likely passed through similar stages billions of years ago. Jupiter and Saturn almost certainly possessed giant circumplanetary disks, while their moons formed from orbiting material. But humans arrived far too late to witness those processes directly. J1407b may represent a rare glimpse into that lost era of planetary evolution, a young giant system still assembling itself. There's something oddly intimate about that realization. We often think of astronomy as studying distant finished objects, ancient stars, stable planets, mature galaxies. But here, perhaps, we're watching a system still growing, still changing, still unfinished. And all of this emerged because one distant star began flickering strangely in 2007. That's one of the most remarkable aspects of science sometimes. Massive discoveries can begin with tiny anomalies. A slight wobble reveals an unseen planet. A subtle distortion uncovers dark matter. A flickering star exposes rings larger than a solar system. The universe hides enormous truths inside delicate signals. Interestingly, the timing of the discovery may have been extraordinarily fortunate too. Giant ring systems like this probably do not last very long by cosmic standards. Over time, ring material gradually forms moons, disperses outward, or falls inward toward the planet. The system evolves continuously, meaning astronomers may have caught J1407b during a relatively brief developmental phase, a temporary moment. That possibility adds a certain emotional texture to the discovery. The rings stop feeling permanent and begin feeling active, transitional, a system in motion rather than a finished structure frozen forever. Imagine visiting a cathedral while construction cranes still surround it, workers moving stone, walls unfinished, scaffolding everywhere. You're not seeing the completed building but the process itself. J1407b may represent something similar on cosmic scales, and the scale truly is difficult to exaggerate. If Saturn possessed rings this large, they would dominate Earth's sky. They would stretch overhead as gigantic luminous structures visible even during daytime. Entire human civilizations would organize mythology and religion around them automatically. The sky itself would look engineered. Yet around J1407b, such structures may genuinely exist. Somewhere in the darkness of Centaurus, trillions of tons of ice and dust orbit a giant world inside layered rings larger than anything humanity previously imagined possible. And the only reason we know about them is because their shadows briefly crossed a star. There's also a wonderful irony hidden here. Humans often associate knowledge with direct vision. Seeing is believing, as the phrase goes. But astronomers rarely work that way. Much of modern astronomy involves inference, reconstruction, mathematical interpretation. Scientists never directly watch the rings move across the star visually. No telescope recorded dramatic footage of giant shadows sweeping through space. Instead, researchers studied tiny brightness fluctuations and carefully asked what kind of structure could create them. It's almost closer to music than photography. You hear echoes and infer the shape of the room, and while the ring interpretation remains the leading explanation, some uncertainty still exists even today. That's important because real science rarely arrives fully completed. Discoveries evolve gradually as new data appears. Models improve, assumptions change, additional observations refine understanding. Astronomers continue searching for repeat transit events from J1407b that could confirm orbital details more precisely. But patience is required, possibly lots of it. The proposed orbit of the object may take many years, and because the geometry is so delicate, repeated eclipses may not align exactly as expected. Astronomy often involves waiting quietly, while the universe continues operating entirely on its own schedule. Still, even with incomplete information, the flickering of J1407 changed planetary science permanently. Because once astronomers realized rings this enormous could potentially exist, new possibilities opened immediately. Maybe giant circumplanetary disks are common during early planetary evolution. Maybe many young giant planets begin life surrounded by enormous moon-forming systems. Maybe our own solar system once looked far stranger than the calm, mature arrangement we see today. The discovery expanded the imagination of planetary science itself, and perhaps most wonderfully of all, it reminded humans that the universe still contains structures capable of surprising us completely. That matters. After centuries of astronomy, after space probes and giant telescopes and thousands of exoplanet discoveries, nature still occasionally produces something so unexpected that scientists briefly sit back and stare at the numbers in disbelief. A star flickers strangely. Astronomers investigate. And suddenly an impossible world begins emerging from the darkness piece by piece. A giant planet wrapped in rings so vast they almost cease feeling planetary at all. And naturally, once scientists realized such a structure might truly exist, another questions immediately followed. What exactly are those enormous rings made of? What exactly would they look like from nearby? Trying to picture the rings around J1407b is a bit like trying to imagine the size of an ocean while staring at a glass of water. Your brain understands the concept intellectually. Water, large amount, very wet. But emotionally, the scale refuses to settle properly. That's the challenge astronomers faced once the data from V1400 Centauri began suggesting the existence of a gigantic ring system. It was one thing to calculate numbers from light curves. It was another thing entirely to ask what such a structure would actually look like if you somehow stood nearby. Because these are not simple smooth hoops floating elegantly around a planet like a child's drawing of Saturn. Real rings are messy, dynamic, layered, alive with motion, and the rings around J1407b appear to operate on such enormous scales that the entire system starts feeling less like planetary decoration and more like a flattened miniature solar system wrapped around a giant world. To begin understanding them properly, we should first clear up a very common misconception about planetary rings in general. Most people imagine rings as solid objects, flat disks, continuous surfaces, something you could theoretically land on if you had enough courage and an extremely questionable understanding of orbital mechanics. But rings are not solid at all. They are made from countless individual particles orbiting together under gravity, ice chunks, dust grains, rocks, debris ranging in size from tiny specks to objects as large as houses or mountains. Saturn's rings, for example, are mostly water ice, bright reflective fragments orbiting in organised bands around the planet. From far away they appear smooth and continuous, but up close they resemble gigantic swarms of orbiting particles. Now take that concept and scale it upward until the entire structure stretches across distances approaching planetary orbits. That's where J1407b becomes difficult to mentally process. The proposed rings likely contain unimaginable amounts of material distributed across dozens of separate bands. Some dense, some sparse, some possibly thick with icy debris, while others remain thin and translucent, and between them lie enormous gaps. Those gaps are particularly important because they may tell us what the rings are doing. Scientists suspect many of these empty regions are being carved by forming moons. As young moons orbit inside the disk, their gravity clears surrounding material, creating paths through the rings much the way snowplows carve lanes through fresh snowfall. Except the snowplows are moons, and the lanes span millions of kilometres. One especially large gap identified in the ring models may indicate a moon roughly comparable in mass to Earth already forming inside the system. Pause for a moment and appreciate how extraordinary that sentence actually is. A moon potentially forming inside rings larger than a solar system around a giant planet hundreds of light years away. Astronomy really does become wonderfully unreasonable after a certain point. What's fascinating is that the rings themselves likely would not appear especially bright from every location nearby. Their appearance depends heavily on viewing angle, lighting conditions, and your position relative to the star. That's true even for Saturn's rings. From certain angles they blaze brilliantly because sunlight reflects efficiently off icy particles. From other angles they become surprisingly thin and ghost-like. J1407b's rings would behave similarly, though on far grander scales. Imagine standing on a hypothetical moon orbiting somewhere within this enormous system. Above you, the sky would not simply contain rings. The rings would dominate everything. They would arch overhead like gigantic glowing highways, stretching from horizon to horizon. Some bands brilliant and luminous, others dark and shadowed. Dense regions might appear almost solid from a distance, while thinner areas resemble translucent veils crossing the stars. And because the rings are so enormous, perspective would constantly shift as the moon orbited the planet. Some nights, vast dark gaps might drift overhead, exposing dense star fields beyond. Other times, bright ring bands could flood the sky with reflected light. You might never experience true darkness at all beneath certain regions. That's one of the strangest consequences of giant ring systems. They become environmental features rather than distant objects. On Earth, the moon influences tides and provides soft nighttime illumination. Saturn's rings, viewed from one of its moons, already create dramatic skies. But J1407b's rings would reshape the entire visual identity of the heavens. Civilizations evolving beneath such skies would probably develop very different mythologies and concepts of the cosmos. It would be impossible to ignore the existence of orbital structures surrounding your world. Gravity itself would become visible. That thought always feels oddly moving somehow. Humans on Earth grew up beneath relatively open skies. We learned astronomy gradually because the solar system largely hides its structure from naked eye observation. Planetary orbits are invisible. Gravity acts silently. But beneath enormous rings, orbital mechanics become part of daily life. You would watch shadows move across ring bands, notice changing brightness patterns, track enormous structures crossing overhead with seasonal regularity. The sky would constantly remind you that you live inside a giant gravitational system. And then there's the texture of the rings themselves. From a distance, they may appear smooth. Up close, they would be astonishingly chaotic. Picture trillions upon trillions of particles orbiting simultaneously, every fragment following its own path around the central planet. Tiny collisions occurring constantly, gravitational interactions rippling outward through the disk. Real ring systems behave almost like fluid environments despite being composed of countless separate objects. Waves propagate through them, density patterns shift, resonances create spiral structures, moons disturb nearby particles much like boats create wakes in water. Inside Saturn's rings, astronomers observe enormous wave formations caused by gravitational resonances with moons. Some ripple patterns stretch thousands of kilometers across, now enlarge that entire system to scales millions of kilometers wide. The rings around J1407b likely contain gigantic gravitational structures moving slowly through the disk over time. The whole thing may resemble an ocean made of orbiting ice and dust. Except unlike an ocean, every particle is moving through vacuum at tremendous speeds, silently. That silence matters. Human imagination often adds sound automatically to large moving things. We picture roaring cosmic storms or thunderous collisions. But space does not work that way. If you somehow floated near J1407b's rings without protective equipment, which would admittedly be an extremely poor life decision, you would see enormous structures moving overhead in total silence. No rushing wind, no crashing waves, only motion. The particles themselves probably vary enormously in composition too. Ice likely dominates many regions, especially if the system resembles young circumplanetary disks elsewhere in the universe. But rocky debris, dust, and more complex materials almost certainly exist throughout the structure as well. Young planetary systems are messy places. Collisions constantly generate fragments. Material migrates inward and outward. Tiny grains interact with radiation pressure from the star while larger bodies respond primarily to gravity. The rings are not static decorations carefully arranged forever. They are evolving environments. And because the system appears young, roughly 16 million years old, things may still be changing rapidly by astronomical standards. That youth is crucial. J1407b likely represents an early stage in moon system formation. Over time, much of the ring material may gradually gather into moons. Some regions could become denser while others thin out dramatically. Eventually, the enormous disk might shrink substantially. What we're seeing now may represent a temporary developmental phase. That possibility changes how we visualize the rings emotionally. They stop feeling permanent and start feeling active, transitional, more like construction than completion. Imagine seeing a city while it's still being built. Cranes everywhere, structures unfinished, roads half-formed, movement and growth visible in every direction. J1407b's rings may resemble that kind of cosmic construction zone, except instead of steel beams and concrete, gravity is assembling moons from orbiting ice and rock. There's another detail scientists find especially fascinating. The ring system appears incredibly thin relative to its width. That sounds impossible at first because the rings are so enormous overall. But planetary rings generally spread outward, far more than they extend vertically. Saturn's rings, despite their huge diameter, are astonishingly thin in many places. J1407b's rings likely follow similar physics, meaning a structure spanning tens of millions of kilometers may still remain comparatively thin overall. It's one of nature's favourite visual tricks: giant flat systems, galaxies, accretion disks, planetary rings. The universe repeatedly forms rotating, flattened structures because angular momentum encourages matter to settle into planes. Gravity loves disks, and occasionally, as with J1407b, gravity creates disks so enormous they almost feel architectural. There's also the matter of colour. What colour would these rings actually appear? That depends heavily on composition and lighting. Ice-rich regions may reflect light brightly, producing pale white or bluish tones similar to Saturn's rings. Dustier areas could appear darker or more reddish. Thin regions might become almost transparent against space, while dense bands glow dramatically when illuminated by the host star. And because the system is so large, lighting conditions across different ring sections would vary enormously. Some portions might lie in shadow while others blaze brightly. Imagine sunrise moving gradually across ring bands millions of kilometers wide. The scale of time itself becomes strange there. Orbital motion inside the system likely produces slow, evolving visual changes that unfold over days or weeks rather than minutes. Everything would feel patient, massive, deliberate. Another remarkable aspect involves the shadows cast by the rings. On moons orbiting within the system, giant ring bands could block substantial portions of starlight. Entire regions might experience regular cooling periods as dense rings passed overhead. Some moons may spend long intervals beneath shadowed skies before emerging again into brighter conditions. In other words, the rings would not simply decorate the environment, they would shape climate, light cycles. Possibly even the evolution of life if habitable moons somehow existed there. That idea sounds wildly speculative, of course, but astronomers increasingly suspect moons around giant planets could someday become important targets in the search for extraterrestrial environments. And if moon systems form inside giant disks like J1407b's, then we may effectively be watching the early stages of those environments assembling themselves. Still, despite all these vivid possibilities, we should remember something important. Nobody has directly photographed the rings in detail. Everything we know comes from interpreting light curves and modelling how different ring configurations affect starlight during transits, which is honestly one of the most impressive parts of the whole discovery. Scientists reconstructed enormous invisible structures from shadows, not because they physically saw giant rings sweeping through space, but because the rings revealed themselves indirectly through patterns of light and darkness. Is rather like reconstructing an entire forest from the movement of shadows on a wall, and perhaps that indirectness makes the rings feel even more mysterious. They exist mostly in the imagination still. Mathematics gives them shape, physics gives them plausibility, but human minds fill in the visual experience. Somewhere out there, beyond our reach, beyond current telescopes, beyond anything humanity can visit for many generations if ever, giant rings orbit silently around a distant world. Ice, dust, rock, moonlets, shadows, all moving together in a delicate gravitational choreography. Human beings are surprisingly bad at understanding very large things. We say words like million, billion, and trillion quite casually now because modern life bombards us with huge numbers constantly. National debts, internet statistics, distances in space, social media followers for people somehow famous entirely because they film themselves reacting to sandwiches. But emotionally, our brains still operate on small ancestral scales. A village, a forest, a mountain, maybe a sea if things get ambitious. Once numbers climb into astronomical territory, intuition quietly gives up and wanders away. And that is exactly what happens when scientists try to explain the ring system surrounding J1407b, because saying the rings are large does absolutely nothing to prepare you for what astronomers actually mean. Even saying they are larger than Saturn's rings barely scratches the surface. That comparison is technically true in the same way that saying the Pacific Ocean is larger than a bathtub is technically true. The scale difference becomes almost absurd. So tonight let's slow down a little and really sit with the size of this thing properly, not mathematically, emotionally. Because somewhere around the moment a ring system starts competing with planetary orbits, the universe stops feeling merely big and starts feeling deeply strange. To begin, let's return briefly to Saturn, humanity's favourite ringed world, and the unfortunate victim of every cosmic comparison since the invention of telescopes. Saturn's rings are enormous by ordinary standards. The main visible ring system stretches roughly 280,000 kilometres across. If you placed Earth beside the rings, our planet would look tiny. You could line up more than 22 Earths side by side across their width. And yet Saturn's rings are considered relatively compact structures in astronomical terms. That's because planets themselves are separated by immense distances. Earth sits about 150 million kilometres from the Sun. Jupiter averages roughly 778 million kilometres away. Space between planets is vast and mostly empty, which is why the estimated size of the rings around J1407b shocked astronomers so profoundly. The proposed ring system may stretch approximately 120 million kilometres across, not the planet, the rings. That means the entire structure approaches the scale of the orbit between Earth and the Sun. Imagine replacing Saturn's familiar rings with something extending outward across planetary distances. Suddenly the word ring starts feeling inadequate somehow. It sounds too delicate, too decorative, like calling the Atlantic Ocean a puddle with ambition. One helpful comparison scientists often use involves our own solar system. If J1407b replaced Saturn while keeping its gigantic ring system intact, the rings would stretch across much of the sky visible from Earth. They would appear vastly larger than the Moon. Daytime visibility would likely be unavoidable. The heavens themselves would look engineered, and importantly, the rings would not merely appear wide, they would contain structure, bands, gaps, dense regions, thin translucent sections. Imagine enormous luminous lanes stretching overhead like gigantic glowing highways crossing the sky from horizon to horizon. Human civilization would never stop talking about them. Every culture on Earth would build stories around them automatically. Religion would change, navigation would change, poetry would become exhausting rather quickly, because every poet would insist on mentioning the rings constantly. And honestly, fair enough. How could you not? What's especially fascinating is that these giant rings may contain enough material to eventually form entire moon systems. That's the key conceptual shift astronomers made when analysing the structure. The rings stopped behaving like ordinary mature planetary rings and began resembling a circumplanetary disk. Essentially a flattened swarm of material where moons are actively assembling themselves. The same process that forms planets around stars may be happening here on smaller scales around a giant planet. Gravity repeating its favourite strategy yet again. And because the system is so enormous, the distances involved inside the rings become difficult to comprehend properly. Moons forming in outer regions might orbit farther from the central planet than Mercury orbits our Sun. Pause there for a moment. A moon orbiting a planet at distances comparable to planetary orbits. That sentence alone feels slightly illegal. Human intuition keeps expecting moons to remain close to planets, because that's what we see in our solar system. But J1407b seems to operate according to entirely different scales. The rings are so vast that they begin functioning almost like a secondary solar system, wrapped around a giant world. And yet despite these enormous distances, the material remains gravitationally connected to the planet itself. That fact always feels remarkable. Gravity reaches astonishingly far. It quietly organises structures across millions of kilometres using nothing except mass and motion. No engines, no guidance systems, just physics, patiently shaping matter over time. One particularly strange consequence of this scale involves orbital periods. Particles in the inner regions of the rings orbit relatively quickly. Farther outward, orbital speeds decrease dramatically. Different parts of the system move according to entirely different rhythms. The outermost regions may take extraordinarily long times to complete full orbits, meaning the ring system is not only enormous spatially, but temporally as well. Motion unfolds slowly there. Patterns evolve gradually across immense distances. Everything about giant structures changes your relationship with time. There's another emotional layer to this too. Humans naturally associate rings with neatness. Circles feel orderly, controlled, balanced. But giant ring systems are not neat at all once you zoom inward. They are chaotic environments full of collisions, resonances, gravitational disturbances, and evolving structures. Inside Saturn's rings, particles constantly crash into each other gently. Waves ripple through dense regions. Moons carve gaps through the disk, now enlarge that entire system, until the rings themselves span planetary-scale distances. The complexity becomes staggering. The rings around J1407b likely contain trillions upon trillions of individual objects interacting gravitationally at all times. Some particles may be microscopic dust grains. Others could resemble mountains in size. Some regions might remain sparse and translucent. Others dense enough to block substantial amounts of starlight. And throughout the entire system, gravity continuously rearranges everything. One of the reasons scientists believe the rings are temporary is precisely because structures this enormous struggle to remain stable forever. Material gradually gathers into moons. Some gets ejected outward. Some spirals inward toward the planet. The system evolves constantly. Which means we may be observing J1407b during a brief developmental stage. That possibility makes the scale feel even more extraordinary somehow, not because the rings are permanent monuments, but because they are temporary moments. Imagine discovering a giant sandcastle, larger than a city, knowing the tide will eventually erase it. The temporary nature enhances the wonder, rather than diminishing it, and by astronomical standards, temporary can still mean millions of years. That's another amusing aspect of space science. Astronomers casually describe structures lasting longer than human civilization as fleeting. A ring system survives for several million years, and scientists respond with something like, "Ah yes, very short-lived." Meanwhile, humans panic when yogurt expires tomorrow. Perspective changes dramatically in astronomy. There's also the issue of visibility from inside the system itself. If you stood on a hypothetical moon orbiting somewhere within the giant rings, the sky would become almost impossible to describe properly using ordinary human experience. The rings would no longer resemble thin bands crossing the heavens, like Saturn's appear from its moons. They would dominate everything. Some portions might appear as gigantic glowing walls stretching across the sky. Other regions would look dark and shadowed where gaps open through the disk. Dense ring bands could block large portions of the host star's light periodically, plunging regions into colder, dimmer conditions before brighter skies returned again. The environment would constantly change as the moon orbited through the system, and because the rings are so enormous, perspective itself becomes strange. Nearby sections might appear detailed and textured, while distant bands fade into luminous arcs crossing the horizon thousands or millions of kilometers away. The entire sky would become a visible map of orbital mechanics. There's something deeply humbling about that image. Humans on Earth live inside a gravitational system too, of course, but most of it remains invisible to us directly. We cannot see Earth's orbit. We cannot watch gravity sculpt the solar system with our eyes alone. Beneath giant rings, however, the structure of the system becomes visible overhead every single day. You would grow up instinctively understanding that worlds move through organized cosmic patterns. The sky itself would teach orbital dynamics. And still, perhaps the strangest part of all this is that nobody has actually seen these rings directly. Everything we know comes from shadows, from light curves, from carefully analysing how V1400 Centauri dimmed back in 2007. Astronomers reconstructed a giant visible structure from changes in brightness. That remains one of the most astonishing aspects of modern astronomy to me. Humanity inferred the existence of rings larger than a solar system around a distant unseen object, because a star flickered strangely for several weeks. The universe whispers. Science listens carefully. And occasionally the answer turns out to be something gigantic beyond expectation. Of course, enormous scale also creates enormous questions. How exactly do structures this large remain organised at all? Why don't the rings simply collapse into moons immediately? What prevents chaos from tearing the entire system apart? One of the most fascinating things about the giant rings surrounding J1407b is that astronomers no longer think of them merely as rings. That sounds subtle at first, but scientifically it changes everything. Because when most people hear the word rings, they imagine something stable and decorative, a finished structure, beautiful bands quietly orbiting a planet forever, like cosmic jewellery carefully placed in position. But the more researchers studied the strange eclipses around V1400 Centauri, the more another possibility emerged. What if these are not mature rings at all? What if we are seeing something earlier, something unfinished, something actively turning into moons, and suddenly the entire system becomes much more than an astronomical curiosity. It becomes a snapshot of planetary evolution itself. To understand why scientists became excited about this idea, we should first talk about how moons probably form in general, because surprisingly, moon formation and planet formation are not all that different. Nature is wonderfully repetitive. Stars form from giant rotating clouds of gas and dust, collapsing under gravity. Planets form inside rotating disks surrounding young stars, and moons, in many cases, likely form inside smaller disks surrounding young planets. The same basic process repeats again and again across different scales. Gravity gathers material together, collisions occur. Tiny particles become larger particles become chunks, chunks become moonlets, moonlets become moons, very slowly, very messily, and with an astonishing amount of crashing into things along the way. Our own solar system almost certainly experienced this stage billions of years ago. When Jupiter was young, it likely possessed a huge circumplanetary disk, a rotating, flattened swarm of material orbiting around it. Inside that disk, Jupiter's large moons gradually assembled themselves from orbiting debris: Io, Europa, Ganymede, Callisto. All those worlds probably emerged from a chaotic rotating disk surrounding a young Jupiter, long before Earth had oceans or even stable continents. The same was likely true for Saturn and its moons. But there's one frustrating problem with all of this. Humans arrived far too late to witness it. By the time astronomy became possible, our solar system had already matured. The violent early construction phase was long over. The giant disks vanished billions of years ago, leaving only the finished moons behind. It's a bit like walking into a cathedral centuries after completion and trying to imagine the scaffolding, noise and chaos that once filled the construction site. You see the final architecture, not the building process. That's why J1407b became so scientifically important, because astronomers may have discovered a system still under construction, and the clues lie inside the rings themselves. When scientists analysed the strange brightness fluctuations from the 2007 eclipse event, they identified evidence for dozens of separate ring bands interrupted by large gaps. Those gaps immediately caught attention, because gaps in ring systems are rarely random. In Saturn's rings, for example, moons and moonlets carve paths through surrounding material. Their gravity disturbs nearby particles, clearing lanes and creating resonances throughout the disk. Tiny moons can maintain surprisingly sharp boundaries inside enormous ring systems. Gravity is remarkably efficient that way. And the gaps around J1407b appear enormous. Some may stretch millions of kilometers wide. One especially large gap may indicate the presence of a forming moon with roughly Earth-like mass already emerging inside the disk. That possibility is extraordinary, not because moon formation itself is rare, but because we may be observing the process while it's still happening. Think about that for a moment. Somewhere more than 400 light-years away, a giant world may currently be assembling its own moon system, while humans watch indirectly through flickering starlight. There's something oddly intimate about it. The universe usually hides its long-term processes from us because cosmic timescales are so vast. Galaxies evolve slowly. Planets form gradually. Moons emerge over immense stretches of time, but occasionally we catch systems in transitional moments. J1407b may represent one of those rare glimpses, and if that interpretation is correct, then the rings themselves are not permanent structures at all. They are raw material, construction material. The giant disk surrounding the planet may eventually shrink dramatically as moons gradually absorb more and more of the orbiting debris. In other words, the rings are temporary because the moons are eating them. Very politely and very slowly, admittedly, but still. Gravity gathers particles together through countless collisions. Small clumps attract additional material. Over time, these growing bodies clear their orbital neighborhoods, leaving behind the gaps astronomers may already be detecting. It's the same process that helped planets form around stars, just scaled down slightly. Although slightly becomes a funny word here because the rings around J1407b are still larger than anything humanity expected around a planet. One particularly fascinating aspect of moon formation involves orbital resonances. As young moons grow inside a disk, their gravity begins influencing surrounding material in highly organized ways. Particles settle into stable patterns. Waves ripple outward through the disk. Gaps widen gradually. The system becomes structured. That structure appears visible in the light curves from J1407b. The brightness changes during the eclipse event suggest not random chaos, but organized layered architecture, distinct ring edges, defined gaps, density variations, all signs of gravitational shaping, and perhaps most intriguingly, signs of a system evolving. Astronomers sometimes compare circumplanetary disks like this to miniature versions of solar systems. That comparison becomes surprisingly accurate around J1407b, because the scales involved are so enormous. Some regions inside the disk may orbit farther from the central planet than Mercury orbits the Sun. Which means hypothetical moons forming there might experience environments more comparable to planets than traditional moons. The distinctions start becoming blurry, and the universe loves blurry categories. We humans prefer neat definitions: planet, moon, ring, star. But nature repeatedly builds objects sitting awkwardly between classifications. Brown dwarfs blur the line between planets and stars. Large moons resemble small planets. Giant circumplanetary disks begin resembling miniature solar systems. J1407b sits directly inside that wonderfully uncomfortable territory. And because the system is so young, roughly 16 million years old, astronomers suspect we're observing it during one of its most active phases. For comparison, Earth is about 4.5 billion years old. That means J1407b is practically an infant by planetary standards. Young planetary systems are violent places. Collisions happen constantly. Material migrates inward and outward. Gravity reshapes everything repeatedly. Nothing is fully settled yet. That chaos matters because moon formation is not gentle. People sometimes imagine planets and moons gradually assembling themselves peacefully from drifting dust. The reality is much more energetic. Objects collide constantly. Some smash apart. Others merge. Giant impacts reshape entire systems. Debris spreads outward and recollects repeatedly. Our own moon may have formed after a Mars-sized object collided with early Earth, throwing enormous amounts of material into orbit. Cosmic construction projects are surprisingly destructive, and somewhere inside the giant disk around J1407b, similar processes may still be unfolding. Moonlets colliding, debris clumping together, orbits shifting gradually, tiny worlds emerging from enormous rings. What's especially beautiful about this scientifically is that moon formation remains difficult to observe directly elsewhere. Circumplanetary disks are faint and challenging to detect. Their scales are usually much smaller than J1407b's enormous structure. But because this system is so gigantic, the ring signatures became visible through the star's strange flickering. The sheer scale of the disk made the process detectable from Earth, and ironically, that same scale may also guarantee the system's eventual disappearance, because giant ring systems like this likely cannot survive indefinitely. Over millions of years, the disk should evolve into a more stable moon system. Material gets consumed, gaps widen, the enormous circumplanetary disk gradually shrinks. Eventually, perhaps only smaller mature rings remain. Saturn itself may once have possessed a vastly larger disk long ago. What we see today could simply be the surviving leftovers after billions of years of moon formation and orbital evolution. That possibility changes how we think about rings in general. Instead of viewing them as static decorations, we begin seeing them as stages in planetary development. Some rings may represent youthful systems still building moons. Others may be remnants left behind after formation largely ended. Some could be temporary debris created by shattered moons or collisions. The universe recycles material constantly. Nothing stays fixed forever. And there's something strangely comforting about that. Even structures spanning millions of kilometers remain part of ongoing processes. Growth, change, evolution. The cosmos is alive with motion everywhere. Another fascinating implication involves habitability. Some scientists wonder whether giant moons orbiting gas planets could potentially support environments suitable for life under the right conditions. In our solar system, moons like Europa and Enceladus already intrigue researchers because subsurface oceans may exist beneath icy crusts. Now imagine giant moon systems forming around planets like J1407b. If large moons eventually emerge there, some might become complex worlds in their own right. Of course, J1407b itself likely sits far too far from its host star for anything Earth-like. But the broader principle matters. Giant circumplanetary disks may be natural moon factories throughout the galaxy, meaning moons could be far more common and diverse than humans once imagined. That's one of the most exciting aspects of exoplanet science generally. Every new discovery expands the imagination of what planetary systems can become. Before the 1990s, humans did not even know whether planets around other stars existed commonly. Now we know the galaxy is overflowing with them. Hot Jupiters, super-Earths, ocean worlds, rogue planets drifting through interstellar darkness alone. And somewhere among them, giant ring systems may quietly assemble moon families around young planets. The universe keeps turning out larger and stranger than expected. Still, we should remember something important. Scientists remain cautious. The evidence for J1407b's rings is compelling, but many details remain uncertain. Astronomers continue refining models of the system, searching for repeat eclipse events, and debating aspects of the object's orbit and structure. That uncertainty is not weakness in science, it's honesty. Real discovery often exists in partially understood territory for years or decades. Nature rarely hands over complete explanations immediately. Instead, humans gradually piece systems together from clues, shadows, light curves, orbital models, tiny fluctuations in distant starlight. And from those clues, a picture emerges. A young giant world wrapped in colossal rings. gaps carved by unseen moons, a possible moon system being born in real time, all unfolding silently in the darkness while gravity patiently continues its work. If these rings are temporary, what eventually destroys something so enormous? One of the strangest things about the universe is that even its most enormous structures can be temporary. That feels counterintuitive at first. Humans instinctively associate size with permanence. Mountains seem eternal because they outlast generations. Oceans feel ancient because they survive civilizations. Giant planets appear unchanging because human lifetimes are too short to notice their evolution directly. So when we imagine the colossal rings surrounding J1407b, our brains naturally want to believe they will remain there forever. Endless glowing bands orbiting peacefully around a distant world for all eternity. But the universe is rarely that stable, especially when gravity becomes involved. And the enormous ring system around J1407b almost certainly represents something temporary. Spectacular, yes. Gigantic beyond expectation, absolutely. But permanent? Probably not. In fact, the very thing making the rings so extraordinary may also guarantee their eventual disappearance. Because giant ring systems are inherently unstable over long stretches of time, to understand why, we need to think carefully about what these rings actually are. Not solid structures, not cosmic sculptures frozen in place, but enormous swarms of orbiting material, ice fragments, dust grains, rocky debris, countless particles moving under gravity's influence around a massive central object. And whenever huge amounts of material orbit together, gravity begins trying to reorganize everything. That's one of gravity's favourite hobbies, honestly. Stars form because gravity pulls gas clouds together. Planets form because gravity gathers debris inside stellar disks. Galaxies form because gravity shapes matter across enormous distances. And inside the rings around J1407b, gravity is almost certainly trying to build moons, which means the rings may already contain the seeds of their own destruction, or perhaps transformation is a better word. Because from the universe's perspective, rings turning into moons is not destruction at all. It's evolution, a system changing shape over time. Imagine a giant construction site slowly consuming its raw materials while buildings rise from the debris. The pile shrinks, but something new emerges from it. That may be exactly what is happening around J1407b. The enormous circumplanetary disk surrounding the planet likely contains vast quantities of orbiting material gradually clumping together through collisions and gravitational attraction. Tiny particles stick, larger fragments grow, moonlets emerge. Over millions of years, these growing moons clear paths through the rings, gathering additional material as they orbit, and eventually, enough material disappears into moons that the giant ring system itself begins shrinking dramatically. We already see smaller scale versions of this process inside Saturn's rings. Tiny moons, known as shepherd moons, orbit within or near certain ring regions, sculpting edges and maintaining gaps through gravitational interactions. Their presence creates order inside the surrounding chaos. Around J1407b, scientists suspect similar processes are occurring on far larger scales. Some of the huge gaps identified in the light curve data may already indicate large moons forming inside the disk, and those moons are not passive passengers. They actively reshape the rings around them. Gravity disturbs nearby particles, alters orbital paths, creates resonances, and gradually clears material from surrounding regions. The more massive the moon becomes, the stronger these effects grow. It's rather like watching giant snowplows move slowly through an enormous blizzard. Except the snowplows are moons, and the blizzard spans millions of kilometers. One especially fascinating aspect of this process involves orbital resonances. When objects orbit together repeatedly in predictable ratios, their gravitational interactions reinforce each other over time. Tiny effects accumulate gradually. Particles become concentrated in certain regions while other areas are emptied. Resonances help create the organized structures seen in many ring systems, but they also contribute to long-term instability, because over immense stretches of time, these interactions rearrange the entire disk. Nothing remains fixed. That's one of the deepest truths in astronomy, actually. The universe loves motion. Everything moves. Galaxies rotate. Stars orbit galactic centers. Planets circle stars. Moons circle planets. Even supposedly stable structures continuously evolve if you wait long enough, and giant rings like those surrounding J1407b contain extraordinary amounts of motion, trillions upon trillions of particles orbiting simultaneously at different speeds depending on their distance from the central planet. Inner regions orbit faster. Outer regions move more slowly. Particles collide constantly. Tiny gravitational disturbances ripple outward through the disk endlessly. The system resembles a gigantic cosmic traffic pattern operating across millions of kilometers, and traffic jams eventually change shape. There's another important problem too: collisions. People sometimes imagine ring particles drifting peacefully without interaction, but real ring systems are incredibly active environments. Particles crash into one another constantly. Most collisions are relatively gentle by astronomical standards, but over time they still matter enormously. Some collisions break particles apart, others help material stick together. Energy gets redistributed throughout the system. Orbital paths slowly change. And because J1407b's rings are probably young and massive, collisions there may occur frequently across the disk. That youth matters enormously. Young planetary systems are chaotic places. Nothing has settled into long-term equilibrium yet. Material still migrates inward and outward. Large bodies continue forming. Orbits remain dynamic. The rings around J1407b likely exist during one of the most active phases of moon system development. And active systems evolve rapidly by cosmic standards. Astronomers estimate giant circumplanetary disks like this may survive only a few million years before transforming substantially. Now, to humans, a few million years sounds comfortably permanent. Human civilization has existed for only a tiny fraction of that time span. Entire species appear and disappear in periods shorter than these rings may survive. But astronomically speaking, a few million years is brief, especially around a young system expected to exist for billions of years overall. That's why scientists often describe structures like J1407b's rings as temporary, not because they vanish tomorrow, but because they represent a short-lived stage in planetary evolution. There's something oddly emotional about that realization. Somewhere out there, giant luminous rings larger than anything humans imagined may currently surround a distant planet. And yet those same rings may already be fading slowly into the future. Moons emerging, material dispersing, the giant disk gradually shrinking over time. The universe builds astonishing things, but it rarely keeps them unchanged forever. Interestingly, even Saturn's rings may not last indefinitely. That surprises many people because Saturn's rings feel iconic and permanent in human culture. But measurements from missions like NASA's Cassini-Huygens suggest Saturn's rings may slowly lose material over time through processes sometimes called ring rain. Tiny particles spiral inward toward the planet under gravitational and electromagnetic influences. Eventually, the rings could thin dramatically or disappear entirely, which means even the most famous ring system in the solar system may be temporary too. J1407 simply operates on much larger and more dramatic scales. There's another force working against giant rings as well: tidal interactions. Gravity does not merely hold structures together, it stretches and distorts them constantly. Large moons interacting with a disk can destabilize certain regions over time. External gravitational influences from the host star may also affect outer portions of enormous ring systems. Remember, J1407b's rings are so huge they approach planetary orbital scales. At those distances, the star itself begins exerting important gravitational influence. That creates additional complexity. Outer ring regions may struggle to remain stable indefinitely because competing gravitational forces pull on the material from different directions. The system becomes a balancing act, a giant gravitational negotiation between planet, star, moons, and ring particles. And over long enough timescales, balance shifts. Some material escapes, some gathers into moons. Some falls inward. The giant disk reorganizes itself continuously. What's especially fascinating is that we may be observing J1407b during a very narrow window of its history. Too early, and the system might have appeared as a chaotic cloud impossible to interpret clearly. Too late, and most of the giant disk might already have transformed into mature moons. But right now, perhaps, we see the system midway through its transition. That timing feels incredibly lucky scientifically. Humans arrived at precisely the right moment in cosmic history to detect giant rings around a distant world while they still exist in this dramatic youthful state. Astronomy often depends on fortunate timing that way. Supernovae explode briefly. Planetary transits align temporarily. Comets appear and vanish. And giant ring systems may spend only limited periods in these spectacular configurations before evolving into calmer, mature systems. The discovery of J1407b reminds us that the cosmos is not static architecture frozen forever in darkness. It is process, movement, change unfolding across scales almost impossible to comprehend. One particularly strange consequence of this instability involves visibility itself. If giant circumplanetary disks eventually become moon systems, then the universe may contain many mature planetary systems whose dramatic youthful rings vanished long ago. Meaning giant ring systems could actually be common in young planets, while remaining rare around older ones. Our own solar system may once have looked far more dramatic than it does now. Jupiter perhaps surrounded by colossal disks, while its moons assembled themselves. Saturn wrapped in enormous luminous bands extending vastly farther outward than today's familiar rings, but billions of years erased those early structures gradually. Humans arrived after construction finished. J1407b may offer a rare glimpse backward into that hidden era. And there's something deeply comforting about the patience of these processes somehow. Humans live fast lives. We rush constantly. Deadlines, schedules, notifications. Meanwhile, gravity calmly spends millions of years reorganizing orbiting ice around a distant planet. No urgency, no panic, just endless gradual transformation. The universe operates according to patience almost everywhere you look. Stars spend billions of years burning quietly. Galaxies rotate slowly across cosmic time. And giant rings evolve one collision at a time until eventually they become something else entirely. Still, despite all this instability, the rings around J1407b remain extraordinarily beautiful conceptually. Perhaps even more beautiful because they are temporary. A structure does not need permanence to possess meaning. In fact, impermanence often intensifies wonder. Sunsets matter partly because they end. Snowflakes matter because they melt. And giant ring systems matter because they evolve. Somewhere around J1407b, countless particles continue orbiting silently tonight. Some colliding gently, some gathering into larger bodies, some drifting slowly toward futures as moons. The enormous disk continues changing even now, while humans lie awake on a small rocky world staring upward and trying to understand it all. What would it actually feel like to stand beneath skies dominated by structures this enormous? Let's imagine for a moment that you are standing on a moon, orbiting somewhere inside the gigantic ring system surrounding J1407b. Not floating in space wearing a heroic spacesuit while dramatic music plays, just standing quietly, feet on frozen ground, a cold wind perhaps moving across dark plains beneath an unfamiliar sky, and overhead, stretching farther than your eyes can comfortably follow, other rings. Not small, elegant bands like Saturn appears through telescopes from Earth. Not distant decorations. These rings would dominate the heavens completely. From horizon to horizon, enormous luminous structures would arc overhead in layered bands wider than entire planetary orbits. Some regions glowing brightly, where icy particles reflect starlight. Others dark and shadowed like giant cracks through the sky itself. The scale would feel impossible at first. Human vision evolved for forests, weather, faces, and nearby landscapes. Our brains are remarkably good at understanding hills, trees, and whether that shadow over there might secretly be a tiger. We did not evolve to process structures tens of millions of kilometers wide suspended above our heads, so the experience would probably feel emotionally overwhelming, long before it felt intellectually understandable. Even Earth's moon already affects humans deeply. People write poetry about it constantly, songs, stories, entire mythologies, and the moon is comparatively small and simple visually. Now imagine growing up beneath giant luminous rings permanently suspended overhead. You would never stop noticing them. They would shape your entire sense of reality from childhood onward. On Earth, the sky often feels open and empty at night. Stars scatter across darkness with huge gaps between them. The heavens appear distant. Beneath J1407b's rings, the sky would feel structured, occupied, layered with visible orbital architecture, and importantly the rings would not remain visually static. That's one detail many people miss initially. Because the ring system is so enormous, different sections would move across the sky gradually as your moon orbited the planet. Bright regions would drift, shadows would shift, gaps between rings might slowly slide overhead over hours or days. The heavens themselves would evolve continuously. Some nights the sky might glow softly from reflected light scattering through icy particles overhead. Other nights, darker gaps in the rings could expose dense fields of stars beyond. You might experience enormous moving shadows crossing entire landscapes, as thick ring bands blocked portions of starlight. Weather itself could be affected. Temperatures might change subtly depending on which regions of the rings passed overhead during orbital cycles. The rings would become part of the environment rather than distant objects. That's the key difference. Here on Earth, celestial bodies feel separate from daily life most of the time. The moon influences tides, certainly, but most people don't consciously feel orbital mechanics shaping their afternoon. Beneath giant rings, however, the sky would constantly remind you that you live inside a gravitational system. Children growing up there would probably learn orbital patterns instinctively long before understanding formal astronomy. They would notice how certain ring bands move seasonally, how shadows shift, how light changes across different cycles. The sky itself would teach them celestial mechanics. And then there's the planet, because above or below the rings, depending on your position, would loom the central giant world itself. Imagine a gas giant many times larger than Jupiter hanging in the sky, while enormous rings stretch around it in layered bands, clouds swirling slowly across its atmosphere, storm systems larger than Earth, rotating beneath glowing arcs of ice and dust. The visual scale would border on psychologically difficult. There are moments even on Earth when landscapes briefly overwhelm human perception. Standing near enormous mountains, looking across oceans, seeing the Milky Way clearly under dark skies, your brain pauses slightly. Something ancient inside you recognizes scale beyond ordinary experience. J1407b's skies would produce that feeling constantly. And yet, despite the grandeur, the actual environment might feel surprisingly quiet. That's important. Human imagination often adds sound automatically to gigantic things. We picture roaring cosmic winds or thunderous celestial machinery, but space remains silent. If you stood beneath those rings without an atmosphere nearby, you would hear nothing from them at all. No rushing, no crackling, no deep cosmic hum, just silence while trillions of particles orbited overhead. That silence somehow makes the image even stranger. Enormous motion without sound. A sky full of visible gravity operating quietly. One especially fascinating aspect involves perspective. Because the rings are so vast, they would not necessarily look curved from every viewpoint. Nearby sections might resemble enormous luminous walls crossing the heavens, while distant portions fade gradually into the horizon. Some regions might appear textured and detailed, others smooth and glowing from far away. Imagine icy rivers suspended across the sky. Now imagine those rivers stretching farther than continents. The human mind would probably struggle constantly with depth perception there. Even Saturn's rings already create strange optical experiences from nearby moons. Depending on lighting and viewing angle, they can appear incredibly thin or overwhelmingly bright. J1407b's rings would amplify those effects dramatically. At certain times, sunlight scattering through icy particles might flood the sky with diffuse glowing light. At other angles, thin ring sections could become ghostly and translucent, almost disappearing against the stars. Dense bands might cast gigantic shadows visible across landscapes below. And because the system likely contains dozens of separate ring layers, the sky would possess incredible complexity. Bright bands, dark gaps, thin translucent structures, dense glowing regions, a constantly shifting layered ceiling stretching across unimaginable distances. There's also a psychological aspect to consider. Humans evolved beneath relatively stable skies. The stars move predictably. The moon cycles gradually. Most celestial patterns repeat comfortably. But beneath enormous rings, the heavens would feel more active somehow. Not chaotic exactly, but alive with visible motion. Orbital mechanics would stop feeling abstract. You would watch them happen overhead every day. Perhaps civilizations beneath such skies would think about time differently too. That's an interesting possibility. On Earth, most people experience time through clocks, weather, biological rhythms and daylight cycles. But beneath giant rings, massive orbital structures might become important markers of seasonal or cultural timekeeping. Certain ring alignments could define calendars. Shadow cycles might structure rituals or traditions. The sky would become not merely scenery, but infrastructure. Ancient human civilizations already built myths around eclipses and planetary motions visible only occasionally. Now imagine living somewhere the entire sky is dominated permanently by giant orbital architecture. Astronomy would likely become central to culture automatically. There's another remarkable detail too. If moons were actively forming inside the ring system, as scientists suspect may be happening around J1407b, then the sky might slowly change over long periods. Not dramatically during one human lifetime perhaps, but gradually enough for civilizations to notice over generations. New gaps widening, bright regions thinning, orbital structures shifting subtly over centuries. Imagine living somewhere the sky visibly evolves across history. That idea feels deeply strange from an Earth perspective because our heavens appear relatively stable across civilizations. The stars remain mostly unchanged over human timescales. But young planetary systems are dynamic places. Things move, grow, transform. And somewhere around J1407b, moons may currently be assembling themselves inside the rings, while giant structures slowly reorganize around them. The sky itself may be under construction. One particularly beautiful possibility involves reflected light. Saturn's rings already reflect substantial sunlight. On some of Saturn's moons, the rings can illuminate landscapes faintly even when the sun sits low. J1407b's rings could produce far more dramatic effects. Large portions of the sky might glow softly during certain orbital alignments. Frozen landscapes could shine under diffuse ring light. Mountains and plains might cast long shadows beneath luminous arcs overhead. Night might never become fully dark beneath dense regions. Instead, there could be gradients of dimness depending on ring position and reflected starlight. The environment would feel layered with light. And all of this emerges from gravity. That's perhaps the most astonishing part. No architect designed these structures. No intelligence arranged them. Gravity simply gathered orbiting particles into organized patterns over time. The same force making apples fall on Earth also builds rings larger than solar systems around distant planets. There's something deeply humbling about that continuity. The universe operates through simple laws producing wildly complex results, and sometimes those results become beautiful almost accidentally. Of course, standing beneath such rings would also remind you constantly of scale. Humans on Earth rarely feel physically small relative to the sky, because our atmosphere softens distance perception. The moon and stars appear approachable somehow despite their enormous remoteness. But beneath giant rings, the visible structures overhead would reinforce cosmic scale relentlessly. You would understand instinctively that you inhabit a tiny part of an enormous gravitational machine, and perhaps that awareness would become comforting after a while. Humans often fear vastness initially, but familiarity changes emotional relationships. Earth's oceans once terrified people too. Mountains felt supernatural. Storms seemed divine. Eventually humans adapted emotionally to those scales. Perhaps civilizations beneath giant rings would feel similarly at home under skies that would completely overwhelm visitors from Earth. Children there might casually point at orbital gaps the way Earth children point at clouds. Teenagers might become bored by ring sunsets despite tourists crying emotionally beside them. That's another wonderfully human truth. No matter how extraordinary an environment becomes, eventually somebody still has to do homework there. Still, I suspect even lifelong residents would occasionally pause and stare upward during especially bright nights. Because some structures remain emotionally powerful no matter how familiar they become. And the rings around J1407b may represent one of the grandest visible structures the universe can naturally produce around a planet. Yet despite all that grandeur, scientists believe these giant rings probably will not survive forever. Over millions of years, the system may gradually transform as moons emerge and the enormous disk slowly shrinks, which raises another fascinating possibility. Could our own solar system once have looked something like this long ago? When most people picture the early solar system, they tend to imagine something fairly tidy. The sun in the middle, planets orbiting politely around it, moons already in place, everything arranged more or less as it appears in textbooks today. Perhaps a few extra asteroids drifting around for dramatic effect. But the real early solar system was not tidy at all. It was chaotic, violent, overcrowded, and astonishingly dusty. In fact, if you could travel backward more than 4 billion years and look at the young giant planets during their earlier stages, there's a very good chance you would not recognize them immediately. Because Jupiter, Saturn, Uranus, and Neptune may once have been surrounded by enormous circumplanetary disks, similar in principle to the giant structure scientists believe may exist around J1407b. Not necessarily identical, not quite as enormous perhaps, but dramatically larger and messier than the calm, mature ring systems we see today. And that possibility changes something important emotionally. Suddenly J1407b stops feeling completely alien. Instead, it begins resembling a glimpse into our own distant past. A younger version of processes that once unfolded around the planets we already know. To understand why astronomers suspect this, we need to think carefully about how giant planets form in the first place. When a young star emerges from a collapsing cloud of gas and dust, it becomes surrounded by a rotating disk called a protoplanetary disk. Inside that disk, planets gradually begin assembling themselves from orbiting material. Tiny dust grains collide, clump together, grow larger, Eventually, after enormous numbers of collisions and gravitational interactions, full planets emerge. But giant planets like Jupiter and Saturn complicate the process because they become so massive that they begin influencing surrounding material dramatically. As these growing giants pull gas and dust inward, they form smaller rotating disks around themselves, circumplanetary disks, miniature versions of the larger stellar disk surrounding the Sun, and inside those smaller disks, moons begin forming much the same way planets form around stars. Gravity repeating its favourite construction method once again. That's the key insight connecting Saturn and J1407b. If J1407b truly possesses a gigantic circumplanetary disk where moons are forming, then astronomers may be observing a stage our own giant planets experienced billions of years ago. We simply arrived too late to witness it directly here. There's something strangely emotional about that idea. Our solar system often feels permanent and mature because it's all humans have ever known. Jupiter appears ancient. Saturn's rings seem timeless. The moons orbit quietly and predictably. But once upon a time, our solar system was young and unfinished too. Jupiter likely wore enormous disks of gas and debris. Saturn may have possessed giant luminous rings vastly larger than those we see today. Moons had not fully formed yet. Nothing was settled. Everything was still becoming something else. And honestly, the early solar system probably looked absolutely ridiculous by modern standards. Collisions everywhere, debris clouds stretching across space, young planets migrating through unstable orbits, objects smashing together constantly. The phrase under construction barely covers it. Astronomers sometimes call this era the age of planetary formation, but emotionally it might be more accurate to call it the cosmic demolition phase, accidentally producing worlds. Because building planets is surprisingly destructive. One leading theory suggests Earth's moon, formed after a Mars-sized object, collided violently with early Earth, ejecting enormous amounts of material into orbit. That debris gradually gathered together into the moon we know today. Jupiter's moons likely formed from giant circumplanetary disks while the planet itself continued growing. Saturn almost certainly possessed far more material around it than survives in its rings now, which leads naturally to a fascinating possibility. Could Saturn once have looked almost unimaginably larger and more dramatic than it does today? Some scientists think yes. Not permanently, of course. Giant disks evolve over time. Material forms moons or disperses. But during its youth, Saturn may indeed have possessed structures approaching the kind of active moon-forming disk now suspected around J1407b. That idea becomes easier to believe once you remember Saturn's current moons. Titan alone is astonishing. Titan is larger than the planet Mercury. It possesses lakes, rivers, weather systems, thick atmospheric haze, and landscapes shaped by liquid methane. It's less a moon and more a full planetary environment orbiting another planet. Then there's Enceladus with its subsurface ocean and giant water plumes spraying into space. Mimas resembling a cosmic snowball someone accidentally hit with a laser cannon. Iapetus with its strange two-tone coloration. Saturn's moon system is enormous and complex, and all those moons had to come from somewhere. Most likely they formed from material once orbiting around young Saturn, which means Saturn probably possessed much more massive surrounding disks long ago. The rings we see today may simply be the surviving leftovers. That thought changes how Saturn feels emotionally somehow. Instead of a finished world with decorative rings, it becomes the age remnant of something once far larger and wilder. Like the worn ruins of an ancient empire whose full scale no longer survives. And Saturn is not alone. Jupiter likely experienced similar stages. Its 4 large Galilean moons, Io, Europa, Ganymede, and Callisto, probably formed inside a circumplanetary disk surrounding the young giant planet. Ganymede itself is larger than Mercury. Again, we are not talking about tiny insignificant objects here. Giant planets produce giant moon systems, and those moon systems require enormous amounts of material during formation. J1407b may simply represent that same process on a much larger scale, perhaps because the planet itself is exceptionally massive, perhaps because the system is extremely young, perhaps because humans happen to observe it during a particularly dramatic stage. The exact reasons remain uncertain. But the broader principle feels increasingly plausible. Young giant planets may naturally begin life wrapped in enormous disks before gradually evolving into calmer, mature systems. There's another important detail too. Our solar system is old, very old, around 4.5 billion years old. J1407b, by comparison, appears to be only around 16 million years old. That's practically infancy on cosmic timescales, which means we are comparing fully mature planetary systems to systems still in early development. It's a bit like comparing a finished oak tree to a sapling and wondering why the branches look different. Time changes everything in astronomy. Ring systems shrink, moons migrate, debris clears away, violence settles into stability. And eventually, after billions of years, systems like ours emerge looking comparatively orderly. But the early stages were probably astonishingly chaotic. One particularly fascinating possibility involves Saturn's current rings themselves. Scientists still debate exactly how old Saturn's visible rings are. Some evidence suggests they may be relatively young, perhaps formed from shattered moons or disrupted icy bodies, rather than surviving continuously since Saturn's birth. If true, then Saturn's current rings may not even resemble its original circumplanetary disk very closely at all. The original giant moon-forming structure vanished billions of years ago. What remains today could be an entirely separate later event. That idea highlights something important. Planetary systems are not static. Even mature worlds continue evolving over immense timescales. Moons break apart, asteroids collide, new rings can form, old rings disappear. The universe constantly recycles material into new configurations, and sometimes, as around J1407b, humans catch systems in transitional moments between one stage and another. There's also a profound shift in scale here. For most of human history, Saturn's rings represented the grandest planetary structure we knew. They became iconic precisely because they seemed almost impossibly elegant and vast. Then astronomy expanded outward into the galaxy. Suddenly Saturn stopped being the end point. Now it may instead represent a quieter, older relative of far larger youthful systems elsewhere. That realization mirrors many discoveries in astronomy actually. Earth once seemed unique. Then we discovered countless planets. The Sun once seemed exceptional. Then we found billions of stars. Saturn's rings once seemed ultimate. Then J1407b arrived wearing something closer to a miniature solar system. The universe repeatedly stretches human expectations outward. And still, perhaps the most moving part of all this is the continuity. The same physical laws shaping distant exoplanetary disks also shaped our own cosmic neighbourhood long ago. Gravity operating patiently across billions of years, tiny particles becoming worlds, disks becoming moons, chaos slowly organising itself into structure. There's comfort in that continuity somehow. Humans often feel disconnected from the universe because space appears so enormous and remote. But discoveries like J1407b remind us that our solar system belongs to a larger family of planetary systems all shaped by the same underlying processes. Saturn's ancient past may still be unfolding elsewhere tonight around distant young planets. And somewhere inside those giant disks, moons may currently be assembling themselves just as Titan and Europa once did around our own gas giants billions of years ago. One especially strange thing to consider is that if humans had existed during the early solar system, the night skies would likely have looked dramatically different. Saturn perhaps brighter and more massive ringed, debris more common, young planets still glowing faintly from formation heat, frequent impacts visible across the solar system. The calm, familiar architecture we know today took immense time to emerge. Which means stability itself is temporary too. Even our mature solar system represents only one stage in an ongoing process. Billions of years from now, things will change again. The sun will evolve. Planetary orbits will shift gradually. Moons may migrate or break apart. Nothing remains fixed forever. J1407b simply allows us to glimpse an earlier chapter in that broader cosmic story. And perhaps that is why the system feels so captivating. Not because it is completely alien, but because it is strangely familiar underneath the scale and mystery. A young giant world wrapped in enormous rings. Moons beginning to emerge from orbiting debris. Gravity patiently shaping matter into new worlds. The same story that once unfolded here long before humans existed to witness it. What hidden physics actually keeps all this enormous material organized at all? At first glance, rings seem simple. Beautiful perhaps, elegant certainly, but simple. A planet sits in the middle, surrounded by flat circular bands, and everything calmly spins around together like a well-behaved cosmic vinyl record. The reality is much stranger, because ring systems are not calm at all. They're environments full of invisible arguments. Gravity pulling in different directions simultaneously, particles colliding constantly, orbital resonances reshaping entire regions, tiny moons acting like gravitational sheepdogs, waves moving through disks of ice and rock without any water involved. And around J1407b, all those strange physical processes may be operating on scales so enormous they border on surreal. One of the easiest mistakes humans make when imagining ring systems is assuming the particles inside them simply orbit together peacefully at the same speed. But that is not how orbital mechanics works. Objects closer to the planet move faster. Objects farther away move slower. Always. This rule appears everywhere in astronomy. Mercury races around the Sun quickly because it sits close to the Sun. Neptune crawls along much more slowly because it orbits far away. The same thing happens inside rings. Particles in inner ring regions complete orbits faster than particles farther outward, which creates an immediate problem. If the rings were solid structures, the inner regions would constantly try to outrun the outer regions, tearing the entire disk apart almost immediately. That's why rings cannot be solid. Instead, they must exist as countless separate particles all following their own orbital paths. And once you realize that, the entire system starts becoming much more dynamic and complicated, because every particle is moving independently. Imagine trillions upon trillions of tiny objects orbiting simultaneously, each responding to gravity slightly differently depending on its location. Now add collisions, now add moons, now add enormous gravitational resonances spreading through the system. Suddenly the rings stop looking like smooth circles and start behaving more like gigantic gravitational weather systems. And honestly, the physics becomes wonderfully weird very quickly. Take orbital resonances, for example. This is one of the most important hidden forces shaping ring systems. A resonance happens when orbiting objects interact repeatedly in predictable ratios. One object might orbit exactly twice for every orbit completed by another object, or 3 times, or 5. Those repeating gravitational tugs build up over time, tiny influences accumulate, and eventually entire regions of a ring system begin reorganizing themselves because of those repeated interactions. Inside Saturn's rings, moons create resonances that generate wave patterns stretching thousands of kilometers across the disk. Certain orbits become unstable, other regions become concentrated with particles. It's rather like pushing somebody on a swing. One push changes little, but repeated pushes delivered at the right rhythm gradually produce large effects. Now imagine that principle operating across ring systems millions of kilometers wide. That may be what is happening around J1407b. The enormous gaps scientists identified in the ring structure likely exist because gravitational resonances and forming moons are sculpting the surrounding material continuously. And the remarkable thing is that astronomers can infer all this from shadows. The strange flickering of V1400 Centauri revealed not just the existence of giant rings, but evidence of hidden gravitational architecture inside them. Invisible physics made visible through structure. There's something deeply elegant about that. Gravity itself cannot be seen directly, but gravity leaves fingerprints everywhere. In ring systems, those fingerprints become astonishingly detailed. Some regions grow dense, others empty out, spiral waves emerge, sharp boundaries appear. The disk organizes itself according to invisible mathematical rules operating continuously beneath the surface, and yet despite all this structure, ring systems remain chaotic environments too. That's because collisions happen constantly. This surprises many people. From a distance, rings appear smooth and peaceful, but up close they are crowded orbital highways full of moving debris. Particles crash into each other all the time. Most collisions are relatively gentle because neighbouring particles tend to orbit at similar speeds, but even gentle collisions matter enormously over long timescales. They redistribute energy, alter orbits, break larger objects apart, sometimes help particles stick together. Ring systems are continuously evolving because of these endless interactions, and inside a giant young system like J1407b's, the collisions may be especially important because moons are likely still forming. That means some collisions build things rather than merely reshaping them. Tiny icy fragments collide and gradually form larger clumps. Larger clumps attract additional material gravitationally. Over time, moonlets emerge from the disk. The rings are not just orbiting, they are manufacturing worlds. Slowly, patiently, one collision at a time. There's another wonderfully strange piece of ring physics too, density waves. These are patterns moving through ring systems somewhat like ripples travelling through water, except the particles themselves do not travel outward with the wave. Instead, the wave is a pattern of compressed and spread out regions moving through orbiting material. Saturn's rings contain many of these structures. Some are triggered by moons, others by resonances, and because J1407b's rings are so enormous, the waves there may operate across truly gigantic distances. Imagine invisible gravitational ripples travelling through icy debris fields, spanning millions of kilometres. The whole system begins feeling less like a ring and more like a living fluid environment. Except everything is happening in vacuum, silently. That silence always feels important somehow. On Earth, large-scale motion usually produces sound. Waves crash, storms roar, rivers rush. But ring systems perform all their complexity quietly. Gravity conducts the entire orchestra without making a noise, and then there are shepherd moons. This is perhaps one of my favourite astronomical terms because it sounds far more wholesome than the underlying physics actually is. Shepherd moons are small moons orbiting near ring edges. Their gravity helps maintain sharp boundaries by nudging nearby particles repeatedly into stable paths. Without shepherd moons, some rings would gradually spread outward and lose definition. In Saturn's rings, moons like Prometheus and Pandora act as gravitational caretakers, helping preserve ring structures. Around J1407b, similar processes may be happening on far larger scales. Hidden moons may already orbit inside the giant disk, shaping enormous ring bands through gravitational interactions. And because the system is likely still young, the moons themselves may continue growing. That's one of the strangest aspects of ring physics. The moons shape the rings feed the moons. Everything evolves together. There's no clean separation between object and environment. Another fascinating force operating inside rings is something called viscous spreading. That sounds alarmingly medical, but it's actually a very important process. Because particles inside the rings collide constantly, angular momentum gets transferred gradually through the system. Inner particles lose energy and spiral inward slightly. Outer particles gain energy and drift outward. Over immense timescales, rings naturally spread apart. Think of it like butter slowly softening across warm toast. Except the toast is millions of kilometers wide and made of orbital mechanics. This spreading helps explain why giant rings may not last forever. Even without moon formation, the rings gradually evolve and disperse through internal interactions. Nothing remains perfectly fixed. The system constantly changes shape. There's also radiation pressure from the star. Tiny dust grains can be pushed subtly by starlight itself. Magnetic fields may affect charged particles. Gas drag inside young systems can alter orbital behavior further. Once you start examining ring systems closely, they become almost unbelievably complicated, and somehow gravity keeps the whole thing organized anyway. That's perhaps the most astonishing part. Out of all this chaos emerges visible structure. Bands, gaps, edges, patterns, order growing from endless motion. One especially important concept in giant ring systems involves something called the Roche limit. This is the distance within which tidal forces prevent material from gathering into larger stable bodies. Inside the Roche limit, gravity from the planet tears objects apart faster than they can fully merge. That's why rings often exist there. Outside the Roche limit, however, moons can form more easily because particles can remain gravitationally bound together. J1407b becomes particularly interesting because its giant ring system likely spans regions both inside and outside these boundaries, meaning some portions of the disk may resist moon formation, while others actively encourage it. The system may effectively contain multiple evolutionary zones simultaneously, certain regions behaving like traditional rings, other regions behaving like moon factories, and all of it operating according to the same underlying gravitational laws. There's something profoundly beautiful about that consistency. The same equations describing falling apples also explain giant ring systems around distant exoplanets. Gravity does not care about scale. The same principles repeat everywhere. Tiny systems, enormous systems, planetary systems, galaxies. The universe keeps recycling similar physical patterns across wildly different environments, and occasionally, as with J1407b, those patterns become visible on scales dramatic enough for humans to notice. Interestingly, the complexity hidden inside ring systems has changed astronomy itself over time. Early astronomers viewed rings as fairly static structures. Now scientists understand them as active, evolving environments full of emergent behavior. In some ways, rings resemble ecosystems. Not biological ecosystems, obviously, but dynamic systems where countless interactions create larger organized structures impossible to predict from individual particles alone. Tiny collisions produce waves. Moons create gaps. Resonances generate patterns. The whole becomes more complex than its pieces, and perhaps that is why giant ring systems feel so captivating emotionally. They reveal invisible forces becoming visible, gravity carving architecture into space itself. Not through rigid structures, but through motion, continuous flowing motion. Somewhere around J1407b tonight, trillions of icy fragments continue orbiting silently. Waves ripple through the disk, moonlets disturb nearby particles, gaps widen slowly over time. The entire system remains alive with hidden physics humans cannot directly see, but can nevertheless understand through careful observation. By this point in the story, it might sound as though astronomers have J1407b mostly figured out. A giant planet, huge rings, possible moon formation, mystery solved. Except not quite. Because the deeper scientists investigate J1407b, the more the system continues behaving like a cosmic puzzle, missing several very important pieces. And honestly, astronomers both love and hate situations like this. On one hand, confusing systems are frustrating. Humans naturally want clean answers. We like complete diagrams, tidy conclusions, and confident explanations. But on the other hand, confusion usually means the universe is teaching us something new. The moment nature stops fitting neatly into expectations is often the exact moment science becomes most interesting. And J1407b has been refusing to behave neatly for years. One of the biggest problems is surprisingly simple. Scientists still have not seen the giant eclipse happen again. That detail matters enormously. The entire discovery of the massive ring system comes primarily from the strange dimming event observed back in 2007 around V1400 Centauri. For nearly 56 days, the star flickered in bizarre patterns, strongly suggesting enormous rings crossing in front of it. But since then, nothing quite like it, and that creates a deeply uncomfortable situation scientifically. Astronomers have an extraordinary set of observations pointing toward a giant ring system. The data fits impressively well. The light curves contain remarkable structure. The ring interpretation remains one of the best explanations available, yet without repeated observations, uncertainties remain difficult to eliminate completely. It's rather like hearing one astonishing piece of music drifting through the fog and then never hearing it again. You know you heard something real. But reconstructing every detail afterward becomes complicated. Scientists suspect the object causing the eclipse may orbit its star very slowly, perhaps taking many years, or even more than a decade to complete a single orbit. That could explain why no identical transit has reappeared yet. But even here, things become messy. Because estimating the orbit depends heavily on assumptions about the system's geometry and speed, and those assumptions themselves depend partly on the ring models. Which means some parts of the explanation rely on other parts remaining correct. Astronomers call this model dependence. Everyone else calls it things getting complicated very quickly. One especially puzzling issue involves orbital stability. The giant ring system proposed around J1407b is so enormous that scientists struggle to explain how it remains gravitationally stable in its current form. Remember, these rings may stretch roughly 120 million kilometers across. That's approaching planetary orbital scales. At those distances, the gravity of the host star itself begins exerting significant influence on the outer portions of the ring system, and this creates tension. Because the farther outward the rings extend, the harder it becomes for the central planet to maintain control over the material gravitationally. Imagine trying to keep an enormous spinning dinner plate balanced, while another invisible force keeps tugging gently at the edges. Eventually, stability becomes difficult. Some researchers suggest the rings must therefore be temporary and rapidly evolving. Others wonder whether the system geometry may differ from initial interpretations. Still others propose the central object itself might be much more massive than originally estimated, and that leads directly into another major uncertainty. What exactly is J1407b? That sounds like a question scientists should already answer confidently, but astronomy often works differently than people expect, especially with distant systems detected indirectly. Most evidence suggests J1407b is probably a giant gas planet many times more massive than Jupiter, but probably remains important there, because the object itself has not been directly observed clearly enough to eliminate all alternatives. Some astronomers think it may instead be a brown dwarf. Brown dwarfs occupy the strange blurry territory between planets and stars. Too massive to qualify as ordinary planets, but not massive enough to sustain full hydrogen fusion like true stars. They exist in an awkward middle category. Nature seems very fond of awkward middle categories. If J1407b is actually a brown dwarf rather than a planet, that changes how scientists interpret the rings and their stability. A more massive central object could potentially support larger surrounding structures gravitationally. But even then, the scale remains extraordinary. The system still pushes the limits of what astronomers expected. Another source of confusion involves the age of the rings themselves. If giant circumplanetary disks evolve relatively quickly, then astronomers may have caught J1407b during a very narrow window of its development. That possibility is exciting scientifically, but statistically awkward, because if these structures disappear rapidly, why did humans happen to observe one now? Are giant ring systems actually common around young giant planets, meaning many systems pass through this stage, or did astronomers simply get extremely lucky? The answer remains uncertain because J1407b is still such an unusual case. There are a few other candidate systems with possible ring structures, but nothing quite as dramatic or well studied, which means scientists lack a large comparison sample. Astronomy becomes much easier when nature repeats itself consistently. One strange object is interesting. 10 strange objects allow patterns. Hundreds produce understanding. J1407b still sits frustratingly close to the single weird thing category. And single weird things are scientifically dangerous because there's always the possibility that some hidden assumption is wrong. Of course, weird things also tend to be where breakthroughs happen. That's the trade-off. Another major complication involves the shape and orientation of the rings themselves. When astronomers reconstruct ring systems from light curves, they rely heavily on geometry. The angle of the rings relative to Earth dramatically affects the observed brightness patterns. Tiny changes in orientation can produce very different transit signals, and because researchers only observed one major eclipse event, multiple geometric interpretations remain possible. Different models can sometimes reproduce similar features in the light curve. Imagine trying to reconstruct the shape of an object after seeing only its shadow once. You can learn a great deal, but ambiguities remain. This uncertainty has led some scientists to debate whether the original ring estimates might even be too large. Perhaps the rings are somewhat smaller but viewed at unusual angles. Perhaps the orbital speed differs from initial assumptions. Perhaps additional structures contributed to the dimming. The core idea of a giant ring system remains compelling, but the details continue evolving as researchers refine their models, and honestly, that's completely normal in astronomy. People often imagine science progressing through clean, straightforward discoveries. Reality is messier. Scientists argue, revise interpretations, challenge assumptions, improve models gradually over years or decades. The public usually sees only the polished final explanation afterward, but the real process resembles a long conversation full of uncertainty. J1407b currently sits right in the middle of that conversation. There's also a technical challenge involving detection methods themselves. Transit observations provide incredibly powerful information, but they also have limitations. Astronomers only see changes in brightness projected along one line of sight. Many details about three-dimensional structure remain difficult to determine precisely. It's a bit like trying to understand an entire city after watching shadows move across curtains. You can infer astonishing amounts from careful analysis, but some uncertainties persist no matter how clever the models become. And then there's the simple fact that young stellar systems are messy environments generally. Young stars fluctuate naturally, dust clouds drift around, debris disks create complicated signals. Separating planetary structures from stellar variability becomes difficult. Astronomers must constantly ask themselves whether the extraordinary explanation is truly necessary, or whether something simpler could account for the observations. So far, the giant ring interpretation continues surviving those tests remarkably well. But the system still refuses to settle neatly into place. One particularly fascinating mystery involves the apparent sharpness of some ring edges. Certain brightness transitions in the light curve occur surprisingly abruptly, implying highly organized structures within the disk. That suggests gravitational shaping by moons or resonances. But maintaining such clean structure across enormous distances is not trivial physically. The rings appear simultaneously chaotic and organized, young and structured, temporary yet remarkably coherent. J1407b constantly balances at the edge between plausible and unbelievable, and perhaps that tension explains why astronomers remain so fascinated by it, because the system keeps forcing planetary science to expand its imagination. Before J1407b, ring systems occupied a fairly modest place in most models of planetary evolution. Important certainly, but secondary. Then suddenly astronomers encountered something operating on scales approaching miniature solar systems. Now researchers must ask entirely new questions. How large can circumplanetary disks truly become? How common are giant moon-forming systems? What determines whether rings survive or collapse into moons? Could some exoplanets possess even larger structures humans have not detected yet? J1407b cracked open a door scientists did not fully realize existed. And once a new possibility appears in astronomy, researchers begin searching everywhere for similar phenomena. There's another deeply human aspect to all this too. Unfinished mysteries keep curiosity alive. If astronomers had already solved every detail surrounding J1407b completely, the system might feel less emotionally powerful somehow. Instead, it exists in that fascinating middle ground between observation and imagination. We know enough to glimpse something extraordinary, but not enough to close the story fully, and the universe often works that way. For every question astronomy answers, new ones appear immediately behind it. Discover planets around other stars, and suddenly humans ask whether they have moons. Discover giant rings, and now we ask how moons form inside them. Solve one mystery, uncover three more. Science is less a staircase toward final answers, and more an endless expanding landscape of better questions. J1407b embodies that beautifully. A young giant world possibly surrounded by colossal rings, a system perhaps building moons before our eyes, a discovery reconstructed entirely from flickering starlight, and yet after years of study, astronomers still cannot say with total certainty exactly what they are looking at. That uncertainty is not failure. It's evidence that humanity has reached the edge of current understanding. Somewhere beyond that edge, gravity continues shaping giant rings in silence, while scientists on Earth keep trying to decode their shadows. And perhaps that is the most wonderful part of all. Even now, after centuries of astronomy, the universe still contains structures capable of genuinely confusing us. By now, somewhere in the back of your mind, J1407b may no longer feel entirely like a planet. Not in the ordinary sense, anyway. Because planets, at least in human imagination, are usually tidy things. Spheres moving calmly around stars, worlds with atmospheres, moons, storms, maybe oceans if we get lucky. But J1407b feels different. It feels unfinished, immense, almost architectural. A giant world wrapped in rings so vast they stop feeling like decoration and begin feeling like an entire environment unto themselves. And perhaps that is why this strange distant system has stayed with astronomers for so long. Not simply because it may contain the largest ring system ever discovered, but because it quietly changes how we think about the universe itself. Before discoveries like J1407b, planetary systems often felt stable in human imagination, finished, ordered. The solar system looked mature and permanent. Planets occupied familiar orbits, moons circled predictably. Saturn's rings seemed eternal, but systems like this remind us that the cosmos is still busy building things, everywhere. Stars are forming right now inside cold molecular clouds. Planets are assembling themselves inside disks of dust. Moons may currently be emerging from giant rings around distant worlds. Nothing truly sits still, and yet somehow, despite all that motion, the universe often appears calm from far away. That contrast always feels strangely beautiful. Enormous change unfolding through extraordinary patience. Gravity does not rush. A moon forms one collision at a time. A ring evolves particle by particle. A planetary system reshapes itself over millions of years with no urgency whatsoever. Meanwhile, humans panic because an email arrived at 9:14 p.m. Perspective shifts a little when you spend time thinking about giant ring systems. There's also something quietly comforting about realizing that complexity can emerge naturally from simple rules. No intelligence designed the rings around J1407b. No cosmic engineer assembled them carefully in darkness. Gravity simply gathered matter together, and over time, structure emerged. Gaps, bands, moons, order appearing from endless motion. The same laws shaping galaxies also shape tiny dust grains orbiting inside distant rings. The same gravity holding your feet to Earth may be helping moons form right now, around a giant world hundreds of light years away. The universe repeats itself beautifully across scales, and perhaps that repetition is part of what makes astronomy feel so emotionally grounding sometimes. Humans often imagine space as cold and alien, but the deeper science looks, the more familiar patterns appear everywhere. Formation, transformation, cycles, things gathering together, things drifting apart, nothing fixed forever. Even the giant rings surrounding J1407b are temporary. That may be the strangest and most moving detail of all. A structure spanning tens of millions of kilometers still cannot last forever. Over time, moons will likely emerge from the disk, material will disperse, gaps will widen. The giant ring system may slowly shrink into something calmer and more stable. Eventually, perhaps, future astronomers somewhere else in the galaxy would look toward this system and see only a mature giant planet with several large moons orbiting quietly around it. The spectacular youthful rings will be gone, or mostly gone, and that idea carries a very gentle kind of melancholy. Not sad exactly, just honest. The universe builds astonishing things, but it rarely preserves them unchanged. Stars evolve, galaxies collide, planets cool, rings disappear, everything exists inside time, even structures so enormous they make solar systems look small. Humans sometimes struggle with impermanence because we instinctively want beautiful things to stay. We want moments frozen, places preserved, familiar skies unchanged. But astronomy repeatedly teaches a different lesson. Change is not separate from beauty. Often change is the reason beauty exists at all. A sunset matters because it fades. Spring matters because winter returns. And giant rings around distant planets matter, partly because they are temporary stages in much larger stories. J1407b exists in a moment. A young system still becoming itself. A world perhaps building moons while humans watch indirectly through shadows and mathematics. That's an extraordinary thing when you really think about it. For most of human history, people looked upward and saw only points of light. Beautiful points of light, certainly, but distant and unknowable. Now humanity can detect rings around worlds hundreds of light years away without ever physically travelling there. We can infer gaps carved by unseen moons, estimate the scale of structures larger than planetary orbits, reconstruct invisible systems from flickering starlight. Not because humans are powerful enough to conquer the universe physically, but because curiosity became precise. Careful observation became understanding. There's something deeply hopeful in that. A small species on a small rocky world learned enough physics to detect moon-forming disks around distant planets. That's remarkable. And still, even after all this progress, the universe remains comfortably larger than our understanding. J1407b continues confusing astronomers. The exact orbit remains uncertain. The full structure of the rings is still debated. Some questions remain unanswered, and honestly, that may be one of the healthiest things about science. There is always another mystery waiting beyond the current explanation. Human knowledge expands, but the horizon expands with it. The universe never fully stops surprising us. Somewhere tonight, while Earth turns quietly beneath sleeping cities and dim apartment lights, and lonely highway gas stations and silent forests, the rings around J1407b continue orbiting in darkness. Ice particles drift through invisible gravitational currents. Moonlets may slowly gather material inside enormous gaps, Shadows move across structures wider than anything humanity ever expected around a planet. All of it silent, all of it patient, and perhaps that's the final feeling this story leaves behind more than anything else. Patience. The cosmos does not hurry itself. Stars take millions of years to form. Planets spend billions of years evolving. Rings emerge and vanish gradually through endless tiny interactions. The universe builds its architecture quietly. Dust becoming worlds. Worlds gathering moons. Gravity shaping matter into temporary beauty over unimaginable stretches of time. And here we are. Brief little creatures made from the same atoms, staying awake late at night trying to understand it all. Trying to map giant rings from shadows. Trying to measure impossible distances. Trying to make sense of the enormous calm machinery surrounding us. There's something strangely comforting about that effort itself. Not because humans will ever fully solve the universe, but because curiosity keeps reaching outward anyway. One flickering star at a time, one strange signal at a time, one impossible ring system at a time, and tonight, as you slowly drift towards sleep, somewhere far beyond Saturn, beyond Pluto, beyond every familiar world humans have ever seen directly, a giant unfinished system continues circling its young star. A planet wearing something larger than a solar system like jewellery, quietly becoming something else.